Hello there, and welcome to Life Beyond Seen, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're taking a slow, quiet dive into one of the deepest and least understood places on our planet. Somewhere in the Pacific, far from the hum of cities and the reach of sunlight, lies a place so remote that for most of human history, it may as well have been another world entirely. It's called the Kermadec Trench, a vast chasm in the seafloor that drops more than 10 kilometers down into darkness. It's a place where pressure could crush steel, where temperatures hover just above freezing, and where life, against all odds, persists. Before we descend into that quiet abyss, I'd love to know something. Where in the world are you listening from tonight? Maybe you're near a coast, maybe hundreds of miles from the sea, but somewhere beyond your walls the Pacific is breathing endless and unseen. If you find comfort in these slow explorations, or if you simply enjoy drifting through science on the way to rest, a like or a subscription would help this little corner of calm reach others who might need it too. Now, take a deep breath and imagine the sound of water pressing gently against itself, stretching endlessly outward. Because beneath that surface shimmer, below the sunlight and the sway of waves, waits a world that has existed far longer than we have, quiet, immense, and almost untouched. The Pacific Ocean is so large that it could swallow all the continents and still have room to spare. It holds more than half of all the water on Earth. When you stand on a shore looking out to sea, what you're really seeing is the start of a descent that could take hours to complete. If you were to dive down, first you'd pass through the sunlit layer, called the epipelagic zone, where most ocean life that we know swims and feeds. Schools of fish shimmer in the light, plankton bloom, and the ocean feels alive with colour. But within a few hundred meters, that brightness begins to fade. The water starts to absorb red, then orange, then yellow light. Blues linger longer, which is why the deep ocean glows in shades of cobalt and indigo. Keep going, and the world grows dim. Shapes blur. The warmth fades away. The surface disappears behind you, and above, the last hints of sunlight dissolve completely. Descending through these layers is like falling through time. Every 100 meters down is another chapter of evolution, a record of how life has adapted to pressure and scarcity. In the twilight zone, creatures begin to glow, not from reflection but from within. Tiny sparks of bioluminescence drift like stars in slow motion. It's easy to think of space when you look at footage from these depths, but the difference is, this darkness is alive. Every flash and flicker is a signal, a warning, or an invitation. The Kermadec Trench lies far deeper than this, down where even the glow of bioluminescence begins to thin. It sits northeast of New Zealand, stretching nearly 1,000 kilometers in length, formed where two immense plates of Earth's crust collide. The Pacific plate is forced beneath the Australian plate, sliding down into the mantle, and the result is a geological wound that cuts into the planet's skin. Its deepest point, known as the Horizon Deep, sinks to about 10,047 meters, almost 7 miles below the surface. To put that in perspective, if Mount Everest were placed at the bottom of the Kermadec Trench, its peak would still be covered by more than a kilometre of seawater. Down there, the pressure is over 1,000 times greater than what you feel at sea level. Any air pocket would be crushed instantly. Metal bends, glass shatters, and yet, somehow, life has carved out a way to exist in that environment. The trench is more than an empty void. It's an entire ecosystem shaped by extremes. Every layer, every microbe, every movement of sediment plays a part in a silent cycle that has continued for millions of years. The Kermadec region itself is a kind of living border. Above the trench runs a chain of volcanic islands and seamounts, part of what's known as the Kermadec Arc. These islands mark the line where the Earth's crust is being dragged down into the depths. Some of them still smoke with volcanic activity, a reminder that the trench isn't just a hole in the ocean floor. It's part of the planet's constant reshaping. Earthquakes ripple through the region as the plates grind against one another. Every tremor sends vibrations up through the water column, small signals that travel across thousands of kilometers. The seabed moves, settles, and moves again. Over geological time, mountains rise and vanish here. The surface of the ocean might look calm, but underneath, the planet is in motion. Scientists didn't even know about the Kermadec Trench until the 20th century. For centuries, the deep sea was considered a lifeless void. The logic was simple: no light, no plants, too much pressure, too little oxygen. It wasn't until deep-sea dredging and sonar mapping began that we started to realise how wrong that assumption was. In the 1950s and 60s, oceanographers began exploring the Mariana Trench, another subduction trench on the other side of the Pacific, and found organisms even at its deepest points. That discovery changed everything. If life could exist there, then it could exist in any trench, including Kermadec's hidden world. Since then, expeditions using remotely operated vehicles and deep-diving submersibles have reached parts of the Kermadec system and found communities of creatures that look like they belong to another planet entirely. Transparent snailfish with delicate, almost ghostly bodies, amphipods the size of small mice scuttling through the sediment, microbes that live by feeding on chemical reactions rather than sunlight. Each new mission reveals something stranger than the last, as if the ocean is reluctant to give up its secrets all at once. It's worth pausing on the sheer physical reality of that environment. The water at those depths weighs so heavily that it forces life to change at a molecular level. Proteins that would unfold under such pressure in surface organisms have evolved to stay flexible. Cell membranes are built differently, using molecules that remain stable even under compression. Enzymes work at near freezing temperatures. Every adaptation is a solution to the same problem: how to keep existing when the universe seems designed to crush you. That kind of resilience feels oddly comforting. Even in a place where sunlight never reaches, something finds a way to survive. The trench itself isn't uniform, it's more like a series of narrow valleys and steep slopes, broken by small ridges. Landslides occasionally tumble down its sides, sending avalanches of sediment into the abyss. These underwater landslides can travel for miles, reshaping the landscape in minutes. Some leave behind scars visible even in sonar maps, massive streaks carved into the seafloor. But most of the time, the trench is still. The sediment settles slowly, grain by grain, forming layers that record the planet's history. Volcanic ash, microscopic shells, bits of organic matter from the surface, all of it drifts downward through the water column like slow-motion snow. It can take months or years for a single particle to reach the bottom, and when it does, it becomes part of a record that stretches back tens of millions of years. If you were to slice through those layers, you could read them like pages in a book, each one a snapshot of Earth's climate, its volcanic outbursts, even its mass extinctions. One of the most fascinating discoveries about the Kermadec Trench is how interconnected it is with the rest of the ocean. Even though it feels isolated, it's part of a global circulation system that links surface and deep waters. Every current, every swirl of plankton, every dying whale that sinks to the seafloor carries energy from the sunlit world above into the dark. When a whale dies and its body drifts down, it becomes what scientists call a whale fall, a sudden banquet for deep-sea life. Dozens of species gather around to feed, scavenging amphipods, worms, and eventually bacteria that break down even the bones. In the trenches, where food is scarce, events like this are monumental. A single whale fall can support an entire community for decades. It's a reminder that even in isolation, the deep ocean is sustained by what happens above. There's something humbling about realizing that the deepest parts of the Earth depend on the surface, just as the surface depends on them. The ocean's depths regulate our planet's temperature and carbon cycle. The creatures down there, invisible and unknown, play a part in keeping our atmosphere stable. They trap carbon in their bodies, bury it in the sediment, and recycle nutrients that eventually rise again. The trench may be hidden, but it's not separate. It's part of the same living system that includes you, me, and every breath we take. Exploration of the Kermadec Trench is still in its early days. Few people have ever seen it directly. The pressure makes human descent nearly impossible, so most data comes from remotely operated vehicles, robotic explorers built to withstand the crushing environment. They carry lights, cameras, sensors, and sometimes small collection arms to gather samples. When one of these machines descends, it takes hours just to reach the bottom. The video feed when it arrives is often grainy, filled with drifting particles that look like dust in a sunbeam. But then, out of that haze, a shape moves, something pale and slow, like a ribbon uncoiling. It might be a sea cucumber or a snailfish, or something we've never named. Every sighting feels like a message from another world. These expeditions don't just expand our knowledge of the ocean, they stretch our sense of what life can be. There's also an emotional side to this kind of exploration that's hard to ignore. When scientists talk about the deep ocean, there's often a mixture of awe and unease. It's not just the danger or the difficulty. It's the realization that we still know almost nothing about most of our planet. Over 80% of the ocean floor remains unmapped at high resolution. The Kermadec Trench is one of the least explored regions on Earth, and yet it's part of the same system that governs weather, climate, and ecosystems across the globe. The unknown isn't far away, it's right below us. The deeper we go, the more we realize how little we've seen. You might think that by now, with satellites orbiting the Earth and robots exploring Mars, we'd have a complete map of our own planet. But the ocean is stubbornly secretive. Light doesn't travel far underwater, and sonar mapping, while powerful, takes time. Each pass of the sonar beam covers a small strip of seafloor, and a trench like Kermadec stretches for nearly 1,000 kilometers. Mapping it in detail can take years. Even then, new features are discovered every time someone looks more closely. Small vents releasing chemical plumes, pockets of unusual minerals, signs of microbial life thriving where, by all logic, there shouldn't be any. It's as if the Earth keeps whispering, "Not yet, there's still more." There's something deeply human about wanting to know what lies beneath the surface. Curiosity has always driven us toward the unknown, whether that's a mountain peak or a black hole. But the ocean has a way of humbling even the most advanced explorers. Every new piece of data comes with 10 new questions. Why do certain species only live at certain depths? How do they reproduce in near total isolation? What role do they play in the global ecosystem? These aren't just scientific curiosities, they're part of understanding how life endures, adapts and continues, even in the harshest environments imaginable. When you think about it, the Kermadec Trench is both alien and familiar. It's alien because it defies our senses. No light, no sound, no colour as we know it. But it's familiar because it's built from the same elements as us. Carbon, nitrogen, water, pressure, energy. The difference is only in degree. We live in one layer of Earth's great gradient, and the creatures of the trench live in another. Neither is more or less natural. They're simply adapted to their own place in the spectrum. That thought alone can change how we see the planet. Not as a surface world with a dark underside, but as a continuous system, connected from sky to core. As the lights of a submersible fade into the distance and the last signal from the surface quiets, the water around grows denser, heavier, stiller. The machines hum, cameras record, data streams upward. Somewhere above, the sun sets, unnoticed by the world below. The descent continues, slow and steady, until the instruments register a flat plane of sediment, the bottom, 10 kilometers down. In the beam of light, tiny creatures drift by, unbothered by our presence. The trench doesn't announce itself. It doesn't roar or glow. It simply is, ancient, patient, and vast beyond comprehension. And just like that, we're here, at the threshold of a world almost no one will ever see firsthand. The story of what lives and moves in this darkness is only beginning to unfold. The surface world fades behind as the descent continues. Above, the waves that once danced in sunlight are now little more than shifting echoes, rippling through layers of water that no longer glisten, only move. There's a point, somewhere between 100 and 200 meters down, where light begins to lose its confidence. It doesn't vanish all at once. It thins, softens, weakens. The reds are the first to go, swallowed quickly by the water. Then oranges fade, then yellows, until only a faint blue glow remains, like the after-image of daylight in a half-forgotten dream. This narrow region where the sea begins to dim is what scientists call the twilight zone, though the name hardly captures its complexity. It's not night and it's not day. It's something in between, a long, slow exhale between two worlds. If you could hover here, you'd notice how the water itself seems to change character. Near the surface, it feels alive with motion. Waves pushing and pulling, sunlight breaking into patterns that dance on every scale. But here, the movement becomes slower, less chaotic, more deliberate. The currents still flow, but they glide instead of crash. Sound travels farther, sharper, cleaner. A single click from a distant whale can echo across kilometers. It's quieter, yet more connected. The ocean at this depth is like a great cathedral filled with invisible voices. This is also the zone where the first true adaptations of darkness appear. Many of the creatures that live here are built for invisibility. Some are transparent, their organs faintly visible behind thin layers of gelatinous skin. Others are silver or mirrored, reflecting what little light remains so that they vanish into the shimmer around them. And then there are those that create their own light, small bursts of bioluminescence flickering from organs called photophores. They use this light for everything: communication, camouflage, even hunting. A fish might flash a signal to attract prey, or a squid might burst into a sudden glow to startle a predator and vanish in the confusion. Every spark you see in this dim world has a purpose. Nothing is wasted here. The Kermadec Trench lies far below, but this twilight region feeds it. Tiny particles of organic matter drift downward from the sunlit surface like slow falling snow, a phenomenon known as marine snow. To us it would look like dust, endlessly sinking, but to the creatures of the deep, it's the foundation of life. Bits of plankton, fragments of dead fish, the remains of algae. All of it drifts through these layers in a silent migration. Some of it is eaten before it can reach the bottom, recycled again and again by small crustaceans and filter feeders. What's left keeps sinking, an unbroken thread connecting the surface to the abyss. In a way, it's the ocean's own economy, where every scrap of energy, every atom of carbon, is used and reused until nothing remains. The twilight zone might seem like a quiet buffer between the bright world above and the dark world below, but in truth, it's one of the busiest layers of the ocean. Every night, billions of animals rise from the depths to feed closer to the surface, and every morning they sink again to hide from predators. This daily vertical migration is the largest mass movement of life on Earth, larger than any land migration, larger even than the flocks of birds that fill the sky. It happens invisibly, every night, all around the planet. Lanternfish, shrimp, jellyfish, and countless others move up and down, following the faint rhythms of light that filter through the sea. When dawn breaks, they retreat again, vanishing into darkness as if the ocean itself were breathing. Inhale, exhale, life ascending and descending in rhythm with the day. What's remarkable is how coordinated this all is without any central signal. No creature is giving orders, no current dictates the pattern. Yet across thousands of kilometers, the same dance unfolds. This synchronization is guided by light, what little there is, and by the internal biological clocks of these creatures tuned over millions of years to the pulse of the planet. Even here, Where sunlight is a memory, its influence still lingers. It's hard not to think of it as a kind of communication between worlds, a reminder that the surface and the deep are never truly separate. The temperature begins to drop sharply here. In the surface layers, the sun keeps the water warm, but just a few hundred meters down, the heat bleeds away. It can fall from over 20 degrees Celsius near the top to just a few degrees above freezing in the twilight depths. The drop isn't gradual. It happens in a band known as the thermocline, where warm and cold water meet. The difference is so sharp that it can act like a barrier, trapping nutrients below and creating a hidden boundary between ecosystems. Some species spend their entire lives above it, others below, and few cross it freely. It's one of those invisible lines that define the structure of the ocean, not through walls or cliffs, but through gradients and transitions. To a human observer inside a submersible, this region would look both mesmerizing and unsettling. The water outside is never still. Small particles drift in the beams of light, giving the impression of movement even when there's none. Every few minutes something glides by, a jellyfish pulsing gently, a ribbon of salp drifting like a translucent chain, or a small fish flashing a pattern of light before vanishing again. There's a strange sense of vastness here. You can't see far, maybe only a few meters, but you feel the immensity of the space. It's like standing in fog at night, knowing there's a world around you but seeing only fragments. Exploring this zone has always been difficult. Nets tear easily, cameras distort under pressure, and artificial lights can frighten the very creatures they're meant to reveal. For decades, what we knew of the mid-water world came from the fragments caught in nets. Broken bodies, crushed jellyfish, delicate animals reduced to nothing more than traces. It wasn't until new technologies allowed for observation without capture that we began to understand just how alive and complex this layer is. The twilight zone isn't empty at all. It's densely populated, just not in the way we expect. The animals here are small, fragile, and perfectly tuned to the faint light that defines their world. They may be invisible to us, but they form the backbone of oceanic life. The Kermadec region in particular is home to an extraordinary range of these midwater species. Because the trench lies so close to volcanic activity and nutrient-rich currents, it supports a vibrant food web even in its mid-depths. Plankton from the surface sink and accumulate, drawing swarms of filter feeders and predators in turn. Scientists studying the area have recorded unexpected biodiversity, species that don't appear elsewhere, suggesting that the trench acts as a kind of isolated evolutionary pocket. The creatures here may have been evolving separately for millions of years, shaped by a mix of cold water, extreme pressure, and limited resources. Pressure at these depths is already immense, dozens of times greater than at the surface, and yet it's still only a fraction of what lies below. Every 10 meters of water adds roughly 1 additional atmosphere of pressure. By 1,000 meters, the weight pressing down is already 100 times what you feel on land. To survive, animals here rely on unique physiological tricks. Many have no air-filled spaces in their bodies, which prevents them from being crushed. Their tissues are gelatinous, almost fluid, which distributes pressure evenly. Some have antifreeze-like compounds in their blood to prevent ice crystals from forming in the near-freezing water. Others rely on slow metabolism, conserving energy in an environment where food is scarce and movement is costly. Every feature is a compromise, a small adaptation carved out by time and necessity. Even the colour palette of life here changes with depth. Near the top of the twilight zone, fish and invertebrates might still show blues and greens, colours that blend with the dim light filtering from above. Deeper down, reds and blacks dominate. In this world, red light no longer exists, so red-coloured animals appear black, invisible to predators. Some deep species are transparent, others opaque and dark as ink. The designs are not for beauty, but for survival. To see them under the artificial glow of a submersible light is to witness something both eerie and oddly graceful. as if evolution itself has been painting in invisibility. One of the most haunting sights captured near the Kermadec region came from a robotic submersible that recorded a cascade of glowing specks drifting upward. At first glance, it looked like a blizzard of light, each particle pulsing faintly before fading. The team later realised it was a swarm of small crustaceans responding to the machine's lights, each producing a defensive flash meant to confuse predators. For a moment, the abyss looked like a sky filled with stars, a brief illusion of reversed gravity. But the lights faded, the movement slowed, and the darkness returned as if nothing had happened. It's moments like that that remind scientists why this work matters, not just for the data, but for the fleeting experience of wonder in a place almost no one will ever see. The transition from light to darkness isn't just physical, it's also symbolic of how human understanding works. We tend to focus on what's illuminated, the parts of the world that are easy to see and measure. But most of reality, from the ocean's depths to the workings of our own minds, exist in shadow. We build instruments, theories, and models to shed light, but the more we illuminate, the more we realise how vast the darkness still is. The Twilight Zone is a perfect metaphor for this kind of knowledge. Not ignorance, but the space in between, where we see just enough to know that there's more. Below this zone, the light dwindles to nothing. Even the faintest glow of bioluminescence becomes rare. The water grows colder, heavier, and more still. Sound travels faster now, yet there are fewer voices to carry it. The deep scattering layer, the dense concentration of migrating animals, fades away, leaving a quieter, emptier expanse. Here the world becomes something else entirely. It's the start of the abyssal realm, where the ocean's weight begins to feel infinite, and the Kermadec Trench opens its unseen mouth. But before sinking that far, it's worth lingering a little longer at this threshold, where the last hints of light still linger. There's a kind of beauty in the transition itself. The surface world, with its noise and colour, depends on sunlight. The deep world, silent and slow, depends on chemistry and chance. The Twilight Zone bridges the two, reminding us that life doesn't obey our boundaries. It adapts, shifts, evolves. It finds the narrow spaces where conditions overlap, and it thrives there. The creatures of this depth are living experiments, proof that survival is often less about abundance and more about balance. When you picture the Kermadec Trench, it's tempting to imagine a single great pit descending sharply into darkness, but it's more complex than that. The trench begins gradually, with the seafloor sloping downward, ridges giving way to valleys, each deeper than the last. Along the way, the Twilight Zone casts its faint influence, light penetrating just far enough to nourish a few drifting organisms that wander too far from the surface. The boundary between this world and the next isn't drawn by a line on a map, but by the slow surrender of light. And once that last trace fades, we pass into a world shaped entirely by darkness and pressure, a world waiting quietly below. The descent doesn't feel abrupt. It's more like easing into sleep, awareness fading one layer at a time. The brightness above grows faint, the noise of waves and life softens. The colours go, leaving only the rhythm of the submersible and the pulse of your own thoughts. In that narrowing band of visibility, before everything disappears, the mind begins to settle. You can almost sense the depth, not as distance, but as weight, as presence. The ocean is no longer something outside you. It feels like something you've entered, a slow, silent continuum that doesn't end, only deepens. And somewhere beneath that calm, beyond the reach of twilight, the earth itself begins to fold. The deeper you go, the slower everything becomes. Motion loses its urgency, and even the smallest vibration seems to hang suspended in the heavy water. The descent from the Twilight Zone into the true deep is a crossing few eyes have witnessed directly. The light fades not in an instant, but in a long, almost imperceptible retreat, until you find yourself surrounded by a darkness so complete that it no longer feels like an absence but a presence of its own. It's not empty. It's dense, patient, and strangely alive. The water thickens with depth, its pressure mounting layer by layer until every cubic inch feels deliberate. The surface is now only a distant idea. Above lies a world of colour, heat, and sound. Below lies something else entirely, a slow, crushing stillness that has lasted for millions of years. At these depths, the ocean reveals its other face. The playful shimmer of sunlight is replaced by a texture of weight and silence. The Kermadec Trench sits ahead, an immense fold in the planet's crust. But even before reaching it, the descent itself becomes a story. Every metre down holds its own ecosystem, its own physics, its own demands. Temperature continues to fall until it stabilises near 2 degrees Celsius, a cold so steady that it feels eternal. Pressure climbs relentlessly, 1,000 tons per square metre at the bottom, compressing water, sediment, and anything that dares to exist. If the ocean surface is a reflection of the sky, this region is its opposite, a slow inversion where time seems to stretch, and the boundary between motion and stillness blurs. Sound becomes the only real sense that carries. Light can't travel here, but sound can, faster and farther than it does in air. Every mechanical groan of a submersible, every ping of sonar, every shifting plate or distant whale song becomes part of a low, continuous murmur. To listen here is to hear the heartbeat of the planet. The deep doesn't roar, it hums, a background resonance shaped by the earth itself. It's a kind of language, one that doesn't use words, just vibration and duration. Few animals inhabit these upper abyssal depths, but those that do seem built from compromise. Everything that could be shed has been discarded. Bones are thin or absent. Bodies are soft, almost fluid, allowing them to bend and flex without breaking under pressure. Movement is rare and deliberate. Many species spend hours or days barely drifting, waiting for small traces of food to fall within reach. Here, energy is a precious commodity. Every motion costs more than it gives, so life has evolved to move as little as possible. The ocean at this depth is not empty, it's economical. Descending through this world, it's easy to forget the scale. The pressure that crushes submarines and warps steel hulls feels abstract when all you can see is blackness. But physics is constant. Every 10 meters adds another atmosphere, another layer of invisible weight. At 1,000 meters, it's like having a small car pressing on every square inch of your body. At 3,000, it's more like a skyscraper. By the time you near the floor of the Kermadec Trench, you're under a pressure of more than 1,000 atmospheres. There's no room for weakness here. Every material, every organism, every molecule has to withstand that relentless compression or be erased by it. The trench itself is born from movement. The Pacific Plate, carrying an ocean of water and sediment, slides beneath the Australian Plate, sinking slowly into the mantle. The process is so gradual that it's invisible in a human lifetime, but over millions of years it shapes continents, builds mountains, and creates valleys deeper than Everest is tall. The Kermadec Trench is one such valley, carved by the unending collision of these plates. Its walls are steep, its floor narrow, and its edges trembling with seismic energy. The trench isn't still. It's always shifting, flexing, adjusting to forces that never stop. Earthquakes here can reach magnitudes that shake the sea itself. When they happen, the sound carries for hundreds of kilometers through the water, a deep rolling groan that speaks of rock grinding against rock. For most of history, this world was completely unknown. Even now, we've mapped only fragments of it in detail. To reach it requires technology that can withstand not only crushing pressure, but also immense distance. A descent to 10 kilometers takes several hours, during which every creak of metal feels personal. Communication with the surface is slow and limited. The water absorbs radio waves completely, so contact depends on long acoustic pulses, like whispers travelling through stone. The further you go, the more isolated you become. By the time you reach the trench floor, you're as removed from the surface as if you'd left the planet entirely. The descent passes through regions with names that sound deceptively gentle. The bathypelagic zone, the abyssal plain, but the reality is stark. The bathypelagic zone begins around 1,000 metres and extends to 4,000. It's here that the last traces of sunlight disappear completely. Above, the twilight fades into black. Below, the pressure multiplies into silence. The few creatures that dwell here seem less like inhabitants, and more like ideas that refuse to die. Long, thread-like fish drift in the water, their bodies almost motionless, using chemical sensors rather than sight to detect prey. Giant amphipods scavenge along the slopes, their exoskeletons flexible yet strong. Sea cucumbers crawl slowly across the sediment, feeding on the fine layer of organic dust that settles from above. It's a world built on patience. The deeper the fall, the more everything slows. Even decomposition becomes sluggish. A dead fish might take months to disappear entirely. The cold preserves, the pressure prevents gas from forming, and the absence of scavengers means that decay is an unhurried process. The bottom of the trench is littered not with skeletons, but with the traces of things that once were. Shapes half erased, outlines pressed into the sediment like faint fossils of the present. It's difficult to say whether this stillness is peace or exhaustion. Down here, the difference feels irrelevant. Scientists studying samples from these depths have discovered that life continues even where it seems impossible. Bacteria thrive in the mud, feeding on chemical reactions between minerals and water. Some of them produce enzymes that only work under high pressure, a trait that vanishes when brought to the surface. Others use methane or sulfur compounds as fuel, performing a kind of chemistry unknown in shallower seas. These microorganisms are invisible to the naked eye, but they form the base of the trench's ecosystem. Without them, the larger creatures wouldn't exist. The deep ocean depends not on sunlight, but on chemistry, an alternate form of photosynthesis powered by the planet's own energy. When exploring the Kermadec Trench, scientists often talk about the sensation of falling endlessly. The walls are so steep that sonar maps look like topographic sketches of mountains turned upside down. There's a point where the slope drops away entirely and the instruments register nothing but a void. That's when you know you've reached the trench proper. The submersible continues downward, its lights cutting through a darkness that feels physical. Every metre deeper, the pressure increases, the temperature stabilises, and the silence thickens. Even the hum of the sub's machinery seems muffled, as though the ocean absorbs sound along with light. There's a certain contradiction in all this. We think of the deep sea as a place of chaos, volcanoes, earthquakes, crushing forces, but what you see, or rather feel, is serenity. Nothing happens quickly here. The trench has no storms, no tides in the way we know them. Currents move so slowly that a piece of sediment might take a century to drift a few metres. If there's turbulence, it's geological, unfolding over millennia. Time itself feels altered. The minutes stretch, and the boundary between past and present softens. Every object, every particle, seems to exist in a state of quiet endurance. There are signs of life even in this stillness. Delicate trails mark where amphipods have crawled through the sediment. Small plumes of disturbed silt hint at unseen movement. Occasionally a translucent snailfish appears, gliding effortlessly through the water. It looks fragile, almost ethereal, yet it's one of the few vertebrates capable of surviving such pressure. Its bones are soft, its flesh rich in compounds that prevent cells from collapsing. It doesn't fight the environment, it becomes part of it. Observing one feels like watching evolution distilled to its simplest form. Life adapting not by resisting, but by yielding. The trench walls are covered with sediment that has been accumulating for eons. Each layer records a different age of Earth's history: volcanic eruptions, ice ages, mass die-offs, all written in microscopic grains. Cores taken from the trench floor reveal a timeline stretching back tens of millions of years. Scientists studying these cores can trace patterns of climate change, ocean circulation, and biological evolution. In this way, the trench acts as an archive, a geological memory that remembers everything even as the world above forgets. When submersibles descend into this realm, they sometimes encounter something unexpected: a faint haze of suspended particles glowing softly in the light beams. It's not bioluminescence, but reflection, the scattering of light by tiny fragments of organic matter. This haze gives the illusion of motion, like dust drifting in a sunbeam, but it's the ocean's slowest snowfall, a constant drizzle of detritus from the surface. Each speck is a story from above, a fragment of plankton, a grain of volcanic ash, a molecule of carbon exhaled by something long dead. The ocean never truly loses its connection to the surface. It just buries it under layers of distance and time. Occasionally, a submersible's sensors pick up vibrations, small rhythmic pulses that suggest life even where no life is visible. Sometimes it's the echo of distant earthquakes, sometimes the subtle motion of gas escaping from the seafloor, and sometimes it's biological, the faint pulse of something moving through the dark. The instruments can't always distinguish between them. In the data, they look almost identical. Perhaps that's fitting. Down here, the boundary between living and non-living blurs. Rocks breathe heat, bacteria feed on stone, and the line between biology and geology dissolves into a continuum of activity. One of the more haunting discoveries made in the Kermadec region is how human influence has reached even this far. Plastic fibres have been found embedded in the sediment at depths exceeding 10,000 metres. They're microscopic, invisible without magnification, but they're there. Fragments of synthetic material carried from the surface by currents and time. Even here, in a place untouched by sunlight, the fingerprints of our species appear. It's a sobering reminder that no part of the planet is truly beyond our reach. The ocean doesn't isolate, it connects. Whatever enters it eventually travels, and even the deepest trenches receive the residue of our civilization. Still, the deep remains largely unspoiled compared to the surface. Its inhabitants have evolved along pathways we barely understand. Some species reproduce only once in a lifetime, releasing a few eggs that drift for years before hatching. Others live for decades, maybe centuries, growing slowly in the cold. There are creatures that generate light without heat, that sense motion without eyes, that breathe not air or water, but chemistry itself. In their presence, our usual categories, fish, insect, plant, lose meaning. The deep sea doesn't conform to the taxonomy of the surface. It invents its own forms. The descent into the trench is both physical and psychological. The deeper you go, the more the mind adjusts to the absence of reference. There's no horizon, no up or down, no distance to measure. Space loses its geometry. The only constants are gravity and the slow pulse of instruments keeping track of depth and time. It's easy to imagine how early explorers, those first scientists who sent probes into the deep, must have felt. A mixture of awe and isolation, suspended between curiosity and insignificance. Every image transmitted from below was a reminder that the world is larger and stranger than we imagine. As the submersible sinks toward the trench floor, small changes appear in the readings. The temperature evens out. The current slows to nearly zero. The sonar begins to map the rising walls of the trench, revealing slopes and ridges carved by ancient landslides. The data shows scars running for kilometers, evidence of entire sections of seabed collapsing into the abyss. These collapses can trigger tsunamis, earthquakes, and plumes of sediment that drift through the water like underwater storms. But in the moment, all is still. The floor approaches, an uneven plain of fine mud, broken occasionally by outcrops of rock or the skeletal remains of marine snow compacted into layers. Touchdown feels almost imperceptible. There's no jolt, no impact, just a faint settling as the craft's weight presses into the sediment. Outside, the lights reveal a landscape that looks alien and yet strangely familiar. It's not barren. Tiny shapes move across the mud, slow as thought. Small burrows mark where life hides. The surface ripples gently, disturbed by the sub's thrusters. For the first time, you can see the bottom of one of Earth's deepest points, a place that has existed unseen since before humanity learned to measure time. Sitting there, surrounded by 10 kilometers of water, it's hard not to feel the scale of it. The trench is not just a feature of geology, it's a frontier of life, a reminder that existence adapts wherever it can. The long fall from sunlight to this quiet floor mirrors the story of the Earth itself, from fiery beginnings to cold persistence. Everything that rises must fall, and in that fall, new forms of life are born. The Kermadec Trench is proof that even the deepest darkness is not the end, but a beginning written in pressure and patience. And so the descent continues, not downward anymore, but inward, into the layers of matter and meaning that define this abyss. The surface world fades completely, leaving only the quiet pulse of the deep, steady and eternal. Somewhere ahead lies the point where the planet folds into itself, and the hidden world begins to take shape. The descent settles into stillness, and then the world begins to shift. Beneath the smooth plain of sediment, the Earth itself is bending. The Kermadec Trench is not merely a deep valley on the ocean floor. It's a living wound in the planet's crust, a place where two immense slabs of Earth meet, and one sinks beneath the other. Here, the Pacific Plate slides under the Australian Plate, descending into the mantle at a rate of a few centimetres per year. That movement sounds small, almost gentle, but across geological time it's relentless. Every inch, every year, builds mountains, forms islands, and drives earthquakes that can shake the ocean to its surface. The trench is the visible edge of that process, a deep, curving scar where the ocean folds in on itself. If you could strip away the water and look directly at it, the Kermadec system would appear as a great arc, stretching nearly 1,000 kilometres northeast of New Zealand. It's part of the Pacific Ring of Fire, the vast chain of trenches and volcanic arcs encircling the ocean. These are the boundaries where tectonic plates collide, diverge and grind together, releasing the planet's internal heat in eruptions and tremors. The Kermadec arc is particularly dramatic. Along its length lie dozens of submarine volcanoes, some active, some dormant, and a scattering of small islands that mark the line where the crust breaks the surface. Each island is a fragment of an ongoing story, built from eruptions that began long before humans appeared and will continue long after we're gone. The trench itself is narrow, barely 60 kilometres across, but its sides rise steeply for thousands of metres. The western wall, where the Australian Plate overrides, is jagged and unstable, cut by faults and ridges that shift under constant stress. The eastern wall, where the Pacific Plate descends, slopes downward into darkness, eventually disappearing beneath layers of rock and sediment that melt into the mantle below. The whole structure moves, bends and flexes as if it were breathing, slowly, invisibly, but continuously. To call it still would be wrong. It's motion disguised as permanence. When scientists study this region, they often describe it as one of Earth's great engines. The movement of tectonic plates here drives both creation and destruction. As the descending plate sinks, it carries seawater, carbon and organic material deep into the planet. The heat and pressure transform these materials into new compounds, some of which rise again through volcanic vents. In this way, the trench connects the surface to the Earth's interior, cycling matter through the crust and atmosphere. The same process that builds islands also recycles oceanic crust. Nothing is wasted. What disappears below eventually returns, reshaped, reborn in lava and ash. It's difficult to comprehend the scale of that transformation. The plates move at about the speed your fingernails grow, yet the forces involved can shift continents. Every few centuries, a major earthquake along the Kermadec subduction zone releases energy equivalent to thousands of nuclear explosions. The tremors travel through the water as sound waves, through the crust as seismic pulses, and through human history as fleeting moments of catastrophe. But most of the time, the process continues quietly, unseen, each day shaping the next. The ocean floor isn't fixed, it's migrating, sinking slowly into the Earth's mantle, while new crust forms elsewhere. The trench marks both an end and a beginning, a boundary where one world gives way to another. When submersibles map the trench walls, they reveal patterns that look almost biological. Folds, fractures, and ridges wind like muscle tissue frozen in motion. Some sections are coated in fine sediment, others stripped bare by landslides that expose ancient rock. Hydrothermal vents dot the slopes, releasing warm, mineral-rich water that supports unique ecosystems. Around these vents, bacteria feed on the chemicals in the water, forming the base of a food chain unlike any on the surface. Tube worms, crustaceans, and other strange organisms gather in dense colonies, living not from sunlight, but from the chemical energy of the earth. This process, called chemosynthesis, turns geology into biology. It's a reminder that life doesn't depend solely on the sun. It can also grow from the heat within the planet itself. These vent communities are fragile, temporary oases in an otherwise sparse environment. When an eruption or a landslide buries one, another appears elsewhere, born from new fractures in the seafloor. The creatures that live there disperse by drifting as lava through the ocean, carried by deep currents until they find another vent. Some of these journeys might take years, even decades. Many never arrive. But the continuity persists, a slow migration sustained by patience. The trench, despite its harshness, is part of a vast network of life that spans the deep ocean, connected by the quiet flow of water and time. The folding of the ocean floor also affects the chemistry of the water itself. As the Pacific plate descends, it drags with it not only rock, but also sediments rich in carbonates and organic matter. These materials release gases as they sink and heat up, contributing to the formation of volcanic arcs above. The gases, carbon dioxide, methane, water vapour, eventually rise through fissures, feeding both underwater and surface volcanoes. This exchange is one of the primary ways the Earth regulates its atmosphere. Over millions of years, subduction zones like Kermadec act as valves, releasing stored gases and cycling them between the ocean and the air. Without these processes, our planet's climate would have evolved very differently. What's fascinating about the Kermadec system is how young it is, geologically speaking. The trench itself is estimated to be less than 10 million years old, a mere blink compared to the 4.5 billion year history of Earth. Yet in that time, it has already become one of the most active tectonic regions on the planet. The islands along its arc, Raoul, Macaulay, Curtis and others, are the visible tips of volcanoes that continue to build and erode with each eruption. Some rise above the sea for a few thousand years, then sink again. Others grow taller with every pulse of magma. The Kermadec arc is, in a sense, a workshop where the planet continually experiments with new forms of land. Above the trench, the ocean currents swirl in complex patterns. The South Pacific gyre sweeps past, carrying warm water from the tropics, while deep currents move in the opposite direction, cold and heavy from the Southern Ocean. The meeting of these currents stirs nutrients upward, feeding the surface ecosystems that, in turn, feed the deep. Storms that form thousands of kilometres away can still send waves that break against the Kermadec Islands. Even the trench, far below, feels their touch in faint pulses of pressure. The ocean is a single body, and even its deepest folds respond to the wind. When researchers deploy instruments into the trench, they often leave them for months or years. Autonomous landers sit quietly on the seafloor, measuring temperature, salinity, and chemical composition. Cameras record slow, continuous footage of the world outside, sediment drifting, creatures passing, nothing much happening in human time, but everything happening in geological time. One year, a team captured a rare event, a massive slump of sediment cascading down the trench wall. It was silent, almost graceful, a slow-motion avalanche that lasted hours. When the cloud finally settled, the instruments were buried under a fine layer of silt. The event had erased part of the landscape and rewritten it instantly. In the deep ocean, change doesn't announce itself. It simply occurs, one collapse at a time. The folding of the ocean floor creates extreme variations in topography. Some sections rise abruptly into ridges, while others plunge into narrow chasms. At certain points, vents release plumes of superheated water, rich in metals like iron, copper, and manganese. As the plumes cool, the metals precipitate, forming crusts and nodules on the surrounding rock. Over time, these mineral deposits accumulate, creating what geologists call hydrothermal mounds. They look like small volcanoes, but instead of lava, they exhale minerals. Some of these structures grow several meters tall, fragile as glass yet enduring for centuries. Around them, microbial mats form, turning bare rock into living tapestry. Every surface becomes a potential habitat. The Kermadec region is also a frontier for studying earthquakes and tsunamis. Because the trench lies so close to New Zealand, seismic activity here poses both scientific interest and real danger. In 2021, a series of powerful earthquakes along the subduction zone triggered tsunami warnings across the Pacific. Fortunately, the waves dissipated before reaching major coastlines, but they served as a reminder of how interconnected the ocean is. A shift in the trench can send ripples that travel halfway around the world. The energy stored in these collisions is immense, and while we measure it in numbers and scales, the ocean experiences it as motion, as rearrangement. The very shape of the seafloor changes, altering currents and ecosystems in ways we're only beginning to understand. One might imagine that the trench is static, but it's more accurate to think of it as an open wound that never closes. The plates continue to converge, the crust continues to dive, and the cycle continues endlessly. This process builds continents on one side and destroys them on the other. Every mountain range, every volcano, every earthquake traces back to these hidden boundaries beneath the sea. The Kermadec Trench is one of the places where the planet reminds us that its surface is not fixed but fluid, constantly renewing itself through both violence and creation. When scientists model these processes, they use terms like subduction, accretion, and uplift. Words that sound mechanical, almost sterile. But the reality is far more dynamic. The trench is not a machine. It's a system in balance, guided by physics but shaped by chaos. Heat, pressure, friction, and time combine to create a landscape that is constantly erasing and rewriting itself. The results are visible not just in maps or data, but in the living record of the islands above. Every grain of sand on Raoul Island, every puff of volcanic smoke, every tremor in the sea floor is connected to the slow bending of the ocean at Kermadec. Despite its remoteness, this region has become a focus for conservation. In 2015, New Zealand announced the creation of the Kermadec Ocean Sanctuary, one of the largest marine reserves in the world, covering over 600,000 square kilometres. The goal is to protect not just the islands but the trench and the vast ecosystems that surround it. Few people will ever visit it, but its preservation matters. Deep-sea environments are vulnerable to mining, pollution and climate change, even when they seem beyond reach. Protecting them is as much about humility as science, recognizing that the planet's deepest places deserve the same respect as its forests or coral reefs. What makes the Kermadec Trench so compelling is that it embodies the full range of Earth's processes in one place. It's geological, biological, chemical, and historical all at once. The folding of the ocean here is a gesture of transformation, a reminder that stability is an illusion. The continents we stand on, the islands we admire, the seas we cross, all are temporary shapes in an ongoing cycle. To see the trench is to witness that cycle in motion, slowed to the pace of the planet itself. In one sense, this folding is destructive. The Pacific plate disappears, swallowed by the mantle, its crust melting and reforming in fire. But in another sense, it's creative. The melted rock rises again to build volcanoes, islands, and eventually new land. The Earth consumes itself to stay alive. The trench is the mouth of that process, where destruction feeds creation. Without it, the planet would stagnate, heat would build, and the continents would stop moving. The Kermadec system is part of the Earth's heartbeat, slow, powerful, and constant. If you imagine standing at the bottom of the trench, 10 kilometers down, surrounded by this immense pressure and silence, the idea that anything could be changing seems impossible. Yet beneath your feet, the crust is shifting, rocks grind and fracture, fluids seep upward from deep layers, carrying the heat of the mantle. The folding is not visible, but it's continuous. Even the smallest tremor is a reminder that the ground itself is alive in its own way. It moves too slowly for the senses, too steadily for fear, but it moves nonetheless. Above, in the islands and seamounts that form the Kermadec Arc, the evidence of that movement is everywhere. Volcanic craters fill with turquoise lakes, cliffs crumble into the sea, and fumaroles hiss quietly in the wind. Raoul Island, the largest of the group, erupts every few decades, reshaping its own landscape. The ash from these eruptions settles on the water, drifts with the currents, and eventually sinks into the trench below. Even the smallest eruption adds another layer to the sediment, another chapter to the planet's memory. The connection between surface and deep is immediate and unbroken. From space, the Kermadec Arc looks like a thin scar curling through the Pacific, barely visible against the vast blue of the ocean. But under that surface, the Earth is folding, constantly writing and erasing its own geography. The ocean doesn't just sit on top of the crust, it participates in its transformation. Every wave, every current, every particle of marine snow is part of the same vast system, cycling matter from sky to core and back again. The trench is simply where that cycle becomes visible in its most dramatic form. Sitting in the deep, surrounded by darkness and weight, it's easy to forget that the planet above is moving. But even here, you can feel the slow rhythm of the fold, the way the Earth pulls and releases, stretches and contracts. The Kermadec Trench is where that rhythm becomes architecture, sculpting the seafloor into impossible shapes. It's the hinge of the Pacific, the line where the world bends and keeps bending, a silent testament to the restlessness of our planet. The longer you stay, the more that restlessness feels natural. The folding isn't violent or ominous, it's simply the way the planet breathes. Over millions of years, the same forces that crush one crust will lift another, the same collisions that destroy islands will create new ones. The trench is not an ending. It's a continuation of everything the Earth has ever done. And as the water presses in, steady and eternal, the motion continues unseen, folding the ocean one quiet centimetre at a time. The deeper the ocean folds into itself, the more it seems to resist the very idea of life. Down here, sunlight is not just distant, it is irrelevant. The water presses with a weight that would crush steel, temperatures hover just above freezing, and food drifts down only as dust. Yet, in this realm that seems sculpted for absence, life persists. Fragile, improbable, but undeniable. Every living thing here is a study in endurance, an experiment in survival under pressure that defies the limits of what biology should allow. It begins invisibly, with bacteria living inside the seafloor itself. They occupy spaces within the sediment, between grains of sand and clay, places so small that the pressure cannot reach them all at once. They feed on chemical reactions, not sunlight, drawing energy from the breakdown of minerals. Iron, sulfur, methane. These are their fuels. In their slow, unseen work, they convert geology into biology. Without them, the deep ocean would be sterile. With them, it becomes something entirely different. A web of microscopic life so vast that it may outnumber all other ecosystems on Earth combined. These bacteria are ancient, descendants of the planet's earliest inhabitants, still thriving where conditions most closely resemble the beginnings of life itself. A little higher above the seafloor, small crustaceans scuttle through the sediment. Amphipods, creatures that look like a cross between shrimp and insects, dominate the trenches. They are built for this pressure, with exoskeletons that bend instead of break, bodies that compress without collapsing. Some are no larger than a grain of rice, others the length of a finger. When scientists first retrieved them from the Kermadec depths, they were astonished not only by their abundance but by their resilience. Even after enduring pressures of 1,000 atmospheres, they remained alive inside sealed traps, moving slowly as if waking from a long sleep. Their diet is as austere as their home. They feed on whatever drifts down from the surface, flakes of detritus, decaying plankton, fragments of larger animals that have died above. Occasionally they find something extraordinary, the remains of a whale, a shark, or a fish carried by currents into the trench. To them, such a find is a feast that can last for months. Hundreds of amphipods will gather, swarming the carcass until nothing remains but bone. The trench floor, usually empty and quiet, becomes a slow-motion storm of activity. When the food is gone, they vanish again into the sediment, waiting for the next fall. The snailfish is another of the trench's improbable inhabitants. It looks delicate, almost translucent, as if built from the same material as the water it lives in, yet it's the most successful vertebrate in these depths. Its body has no air-filled cavities, no rigid bones that could shatter under pressure. Its flesh is soft and flexible, its skin smooth and unscaled. The snailfish moves slowly, almost lazily through the water, feeding on small crustaceans and worms. It doesn't need to chase. Its world has no urgency. Everything here happens at a pace dictated by scarcity. When researchers from the University of Aberdeen sent cameras into the Kermadec Trench in 2017, they recorded footage of snailfish gliding effortlessly across the bottom, their pale shapes ghostly in the artificial light. They seemed unbothered by the presence of the cameras, continuing their quiet drift as if unaware of being observed. Each movement was measured, each flick of the tail deliberate. Watching them, it was hard not to feel that they belonged here, in a way nothing from the surface could. The deep ocean doesn't reward strength or speed. It rewards balance, patience, and an almost meditative stillness. Even smaller forms of life thrive in this crushing dark. Foraminifera, tiny single-celled organisms encased in shells, cover the sediment like a microscopic city. They feed on the organic snow that drifts down from above, leaving intricate patterns in the mud as they move. Each shell, when viewed under a microscope, is a marvel of design. Spirals, chambers, and ridges shaped with mathematical precision. Their structures have survived for hundreds of millions of years, fossilized in rock layers across the planet. In the Kermadec Trench, they continue the same work they began in the Cambrian seas, building, feeding, dying, and leaving traces that record the planet's slow history. Microbes cling to every surface, even the rocks that form the trench walls. Some of these microbes live in biofilms, thin layers that shimmer faintly under light, composed of billions of cells cooperating in silence. They feed on hydrogen and methane seeping from the seafloor, producing waste that, in turn, feeds other species. In this way, the entire trench functions as a closed circuit. Nothing is wasted, not even decay. When an organism dies, bacteria consume it, releasing nutrients that sustain others. The cycle continues endlessly, a slow, invisible metabolism that keeps the abyss alive. It's easy to think of the deep ocean as static, but in reality it pulses with chemical and biological energy. Methane bubbles rise from fissures, carrying with them the scent of Earth's interior. Small plumes of warm water escape from cracks in the crust, creating microhabitats just a few degrees warmer than their surroundings. In these tiny temperature gradients, life finds its foothold. Some bacteria cluster near the vents, thriving on the chemical richness. Others float freely in the water, carried by currents that shift over years rather than days. For them, motion is destiny. They go where the ocean takes them, surviving not through control but through endurance. The absence of light shapes not only how creatures look, but how they sense their world. Eyes are useless here, so evolution has replaced vision with other senses. Many deep-sea animals have pressure-sensitive organs capable of detecting vibrations in the water. Others use chemical receptors to sense prey or mates. Some generate their own light, communicating through flashes and patterns that to us seem random but to them carry meaning. A slow pulse might signal territory. A quick flicker might be a mating call. A sudden burst of light might be a distraction, a way to escape predators. In a place where sound is rare and sight is impossible, light becomes language. Bioluminescence is perhaps the most striking adaptation of the deep. It's a form of life's rebellion against darkness. Tiny plankton glow when disturbed, leaving trails of greenish light that mark the path of movement. Jellyfish pulse with blue or violet hues. Certain fish carry rows of photophores along their bellies, mimicking the faint light from above to render themselves invisible from below, a trick known as counter-illumination. Even predators use light, dangling glowing lures to attract the curious or the hungry. In the Kermadec depths, the light show is subtle, brief, and purposeful. Every flash is a negotiation between survival and exposure. Researchers studying bioluminescence in trench organisms have found that the chemistry behind it is remarkably efficient. The light is produced through reactions between luciferin molecules and oxygen, catalyzed by enzymes known as luciferases. Unlike artificial light, it generates almost no heat, a perfect adaptation in a place where energy is scarce. The glow can be turned on or off in milliseconds, allowing animals to communicate or hide as needed. In a world without day or night, these flickers form the only rhythm that matters. There's a strange intimacy in knowing that the deepest parts of the planet are filled with these small living lights. They flicker unseen, illuminating nothing but each other, tracing patterns we'll never fully decipher. It's humbling to imagine how much life happens beyond perception. Every second, millions of these exchanges occur in the dark, unnoticed but essential. The ocean's surface may host the drama of weather and waves, but its true heart beats here, quietly, far below the reach of sunlight. When scientists retrieve sediment cores from the trench floor, they often find traces of organic carbon buried deep within. These traces are the remains of life that fell, was consumed, and then preserved. Each layer tells a story of abundance or scarcity, of warmer or colder ages, of shifts in the planet's balance. The organisms that live in the trench contribute to this record simply by existing. Their bodies become data written in mud, storing information that will outlast civilizations. In this way, life in the deep isn't just surviving, it's recording, archiving the memory of Earth in chemical form. But survival here comes at a cost. Growth is slow, reproduction rarer still. A snailfish might live for decades, producing only a handful of offspring. An amphipod might spend years before reaching maturity. Food scarcity dictates the tempo of life, and that tempo is glacial. In the crushing dark, efficiency replaces abundance. Nothing grows quickly, nothing wastes energy. Even death happens quietly, absorbed into the cycle before it can decay. Exploration of this world remains a challenge. The pressure destroys most equipment within minutes. Cameras must be encased in titanium, lights built to withstand temperatures near freezing and crushing loads that would flatten any surface device. When a probe descends, it takes hours to reach the bottom, and communication with it is slow, each signal delayed as it travels through water. What we know of the trench's inhabitants comes from brief glimpses, grainy footage, samples retrieved by chance, fragments of DNA caught in the water. Each discovery feels like a whisper, a fragment of a larger conversation we're only beginning to understand. One of the most surprising findings from the Kermadec region was the presence of amphipods containing plastic compounds in their bodies. These creatures, living in one of the most remote environments on Earth, had ingested microplastics that had drifted from the surface. It's a grim reminder that even here, life cannot escape the consequences of the surface world. The same currents that carry food also carry pollution. The ocean connects everything, and nothing we release into it ever truly disappears. Yet, even so, life endures. The amphipods continue to feed, reproduce, and adapt. They embody the resilience that defines the deep sea, a capacity to persist even when the world above changes beyond recognition. There's something profoundly humbling in that resilience. We tend to think of life as fragile, dependent on narrow conditions, but the deep ocean tells a different story. Life is not delicate, it's tenacious. It finds ways to exist where logic says it shouldn't. It thrives not in spite of pressure, but because of it, using the very forces that seem destructive as the foundation for stability. The creatures of the trench are not survivors of catastrophe. They are the baseline, the constant reminder that existence is possible anywhere patience outweighs haste. If you could drift here long enough, you might start to notice the rhythm of this world. The slow fall of particles, the faint movements of unseen creatures, the occasional vibration from a distant quake. It's not silence, not really, just a different kind of sound, one made of long intervals and faint echoes. The trench is never still. It moves on a timescale that makes our sense of time seem frantic. The deep has no seasons, no dawns or twilights, only the steady persistence of being. And yet, for all its strangeness, this world feels connected to us in subtle ways. The carbon that falls here once flowed through forests and animals on the surface. The water that fills this trench once rose as vapour from the sea and fell as rain. Even the creatures of the deep, though alien in form, share the same biochemistry as us, the same DNA, the same molecular machinery. The difference lies only in the adaptation shaped by environment. In that sense, the life beneath the Kermadec Trench isn't separate from ours. It's an extension of the same story, written under pressure instead of light. The crushing dark is not a void. It's a habitat, one that reveals how little we truly understand about what it means to live. Here, biology stretches to its extremes, and the boundaries between survival and existence blur. The amphipods, the snailfish, the microbes, they're all part of a slow ancient conversation between matter and motion, energy and time. They show that life doesn't need comfort, warmth, or even light. It only needs opportunity, however small, and enough time to adapt. Somewhere deep within the trench, another amphipod grazes on a fragment of organic matter that's been falling for months. A snailfish glides past, its body undisturbed by the weight of 10,000 meters of water. Microbes pulse quietly in the sediment, feeding on invisible chemistry. Everything moves in rhythm, unhurried, unending. This is not the ocean's desolation, it's its endurance, its steady assertion that life will find a way to persist wherever the planet allows it, no matter how cold, how dark, or how deep. The light from the submersible fades, swallowed by distance. The cameras record their final images before the power begins its slow ascent back toward the surface. But the world below doesn't notice. It doesn't depend on witnesses. It will continue exactly as it has, unseen, patient, perfect in its slowness. Down here, in the crushing dark of the Kermadec Trench, life keeps breathing quietly, turning pressure into peace. Pressure is a strange sculptor. It destroys and creates in the same gesture, reshaping everything it touches until only what can endure remains. Down here in the depths of the Kermadec Trench, pressure isn't simply a force, it's a condition of existence. It presses from every direction, an invisible weight that defines what can live, how it lives, and even what life means. If gravity holds us to the planet, pressure holds the deep ocean together. It is the quiet, constant alchemy that turns the impossible into the ordinary. At the surface, it's easy to think of pressure as something external, something that can be measured, resisted, or overcome. But in the deep sea, it isn't an adversary. It's part of the environment in the same way that light and air are for us. Every organism here is built around it. The water doesn't simply surround them, it inhabits them. Their cells, membranes, and molecules are all shaped by its presence. To exist here is to be in equilibrium with compression itself, to have every part of your being adjusted to match the weight of 10 kilometers of ocean overhead. The numbers almost lose meaning at these depths. For every 10 meters of descent, pressure increases by 1 atmosphere. At the bottom of the Kermadec Trench, that's more than 1,000 atmospheres pressing on every square centimetre. Imagine the weight of 50 jumbo jets concentrated on the surface of a single human body. No air bubble could survive it. No lung could expand. Metals that seem rigid on the surface bend and groan. Even water itself, which we think of as incompressible, yields slightly under that kind of force. Its density increases, its behaviour shifts, its sound carries differently. In the deep, the ocean becomes a substance almost unlike the one we know, denser, heavier, and older in its feel. To understand how life survives here, scientists have had to redefine the very notion of adaptation. It's not about resistance. Nothing resists pressure. It accepts it. Deep-sea life has evolved to match its surroundings molecule by molecule. Proteins, the molecular machines that drive every biological process, behave differently under pressure. In surface organisms, these proteins rely on delicate folding patterns to maintain their shape and function. Under extreme compression, those patterns collapse and the proteins unravel. For creatures of the trench, evolution has rewritten this rule. Their proteins contain special amino acids and stabilizing molecules known as piezolites, chemical compounds that protect their structure under immense force. Without these piezolites, cellular life would crumble in seconds. With them, cells remain flexible, stable, alive. These protective compounds act almost like molecular cushions. They prevent the hydrogen bonds within proteins from collapsing and allow enzymes to function normally even under conditions that would destroy any surface species. In the Kermadec depths, one of the most common piezolites is trimethylamine N oxide, or TMAO. It's the same compound that gives many deep-sea fish their distinctive odour when brought to the surface. The deeper the organism lives, the higher its concentration of TMAO, which stabilizes proteins by counteracting the effects of pressure on water molecules. This relationship is so consistent that scientists can often estimate an animal's habitat depth simply by measuring how much TMAO is in its tissues. In a sense, chemistry itself keeps the record of depth. Pressure doesn't only shape biochemistry, it sculpts form. The animals of the deep are soft not by accident but by necessity. Rigid structures create weak points where pressure can concentrate and cause collapse. Flexibility, not strength, is the secret to survival. That's why many trench dwellers appear gelatinous, almost ethereal. Their bodies are composed mostly of water, matching the density of their surroundings so perfectly that they neither sink nor rise. Some have lost bones altogether. Others possess skeletons made of cartilage so thin it's nearly transparent. Muscles are sparse, organs minimal, and movement economical. What would seem fragile to us is, in truth, the pinnacle of adaptation. To live here is to yield without breaking. This equilibrium between the living and the crushing weight around it is an elegant kind of compromise. It blurs the line between the external world and the internal one. Pressure becomes not an enemy but an element, a partner in the ongoing experiment of existence. The snailfish that glides through this darkness doesn't resist the pressure pressing on its body. Its tissues are filled with the same water that surrounds it, and its internal pressure matches the external exactly. It doesn't fight the environment, it is the environment. Every deep-sea organism lives by this same principle. The deeper the world around you presses, the more perfectly you must match it. Even the mechanics of reproduction and growth are governed by this rule. In the deep sea, eggs and embryos develop slowly, often over months or years. The process of cell division takes longer under pressure, and enzymes that control DNA replication work at reduced speeds. Growth is deliberate, meticulous, and timed to the rhythm of the environment. For species that rely on drifting larvae, the challenge is even greater. Most larvae are buoyant, built to float upward towards shallower waters, but for trench organisms, rising even a few hundred meters could be fatal. Their young must remain near the same pressure at which they were conceived, or their cells will rupture. Some species solve this by encasing their eggs in dense gelatinous material that prevents them from drifting. Others rely on live birth, ensuring their offspring never face the shock of changing pressure. Life here doesn't take chances. It plans for equilibrium from the first moment of existence. When scientists first attempted to bring deep-sea organisms to the surface for study, most of them died before reaching the light. The sudden loss of pressure caused their bodies to expand, cells to burst, and internal gases to explode outward. It wasn't until researchers built pressure-retaining recovery chambers that they could observe living specimens without destroying them. What they found was remarkable. Under their native conditions, these creatures were perfectly normal, calm, active. Only when removed from their world did they seem fragile. The deep doesn't create weak life, it creates precisely tuned life. Its fragility is an illusion of perspective. Pressure also alters the physics of sound, light, and matter. At the surface, sound travels about 1,500 meters per second through water, but at the depths of the Kermadec trench, where the temperature is near freezing and the density much higher, it moves faster and more efficiently. This allows sounds from earthquakes, volcanic eruptions, and even distant storms to propagate over immense distances. Hydrophones placed near the trench have recorded rumbles and clicks that originate hundreds of kilometers away. The deep ocean is like a cathedral of echoes, every vibration resonating through layers of water. The pressure doesn't silence the world, it amplifies it, carrying its low notes farther than air ever could. Even light behaves differently under compression. Artificial lights from submersibles scatter less, but penetrate only a short distance before being absorbed completely. To the human eye, the deep appears infinite, but to the creatures who live here, it's defined by gradients of shadow. Many species have evolved to perceive faint traces of bioluminescence or the soft glow of decaying organic matter. Some can detect polarization of light, a sensitivity unknown in most land animals. They navigate not by sight in the way we understand it, but by detecting subtle differences in the faintest glimmers around them. Their perception is sculpted by darkness and pressure working together, teaching them to see where sight should be impossible. Chemistry, too, changes its rules here. The increased pressure alters the behavior of water molecules, compressing them into arrangements that affect how substances dissolve and react. Gases behave differently. Oxygen becomes more soluble, while carbon dioxide forms carbonic acid more readily. This shift in chemistry influences the metabolic processes of all living things below. Enzymes that would fail in our conditions operate perfectly here, tuned to the narrow range of temperature and pressure that defines the trench. It's as if the laws of biology rewrite themselves under the weight of the ocean, creating a parallel version of a life's chemistry where equilibrium replaces fragility. Pressure even influences evolution in ways we're only beginning to grasp. The genetic sequences of trench organisms reveal mutations and adaptations found nowhere else. Some of these genes encode for pressure-resistant proteins, others for metabolic pathways that can function with minimal oxygen. There are even hints that the immense pressure affects DNA itself, influencing how it coils and replicates. Life in the deep evolves slowly but precisely, each change tested over millennia by the relentless force surrounding it. The result is not diversity in numbers, but in specialization. Every organism is a masterpiece of compromise, existing at the narrow intersection of what is possible and what is necessary. To humans, pressure is synonymous with stress, with the idea of being overwhelmed. But in the ocean, it becomes something entirely different, a stabilizing force. Without it, the deep's fragile balance would unravel. The very stillness of the trench depends on it. The dense, cold water pressed into the Kermadec abyss doesn't circulate easily. It remains there for centuries, layered like time itself. Within those layers, pressure keeps the chemistry steady, the temperature constant, and the silence unbroken. Without it, the ocean's deep calm would vanish. The crushing weight above isn't the enemy of stillness, it's the reason for it. In many ways, the story of pressure in the deep sea mirrors the story of adaptation in our own lives, though the comparison isn't a matter of metaphor but of structure. Life anywhere, on land, in the air, or under 10 kilometers of ocean, exists by adjusting to constraints. It doesn't escape them, it integrates them. Just as deep-sea creatures grow soft to survive compression, we evolve mental and social adaptations to survive the forces that press on us. It's a reminder that resistance is not the only way to endure. Sometimes the most profound resilience comes from alignment rather than defiance. Back in the Kermadec region, instruments left on the trench floor continue to record data. Pressure sensors detect subtle fluctuations, tiny tremors caused by distant quakes, passing internal waves, or shifting sediments. The numbers barely change, yet each variation tells a story. The weight of the ocean isn't static. It moves slightly with tides and atmospheric pressure above. Even the moon exerts its pull here, though its influence is measured in millimeters. The Earth breathes through these patterns, and the trench listens, translating that rhythm into data we can only interpret from afar. What's fascinating is that pressure doesn't just compress, it preserves. Objects that sink to the trench can remain intact for astonishingly long periods. Shipwrecks, debris, and even organic material decay at glacial rates. The cold and lack of oxygen slow bacterial activity, while the weight above prevents disturbance. The result is a kind of natural archive, where remnants of the surface world remain suspended in time. The deep holds its history as it holds its life, quietly, under layers of stillness and compression. Even human-made machines must obey the deep's laws of adaptation. Submersibles capable of descending into the Kermadec trench are built like living organisms, rounded, flexible, pressure-balanced. Spheres are favoured over cylinders because they distribute force evenly, much like the cells of trench creatures. Engineers fill certain compartments with incompressible fluids to prevent collapse, mirroring the biology of the organisms they study. The deeper we explore, the more our technology begins to resemble the life it seeks to understand. Survival here, whether mechanical or biological, depends on surrendering to pressure, not fighting it. Every few years, researchers deploy free-falling landers into the trench. These autonomous instruments drop slowly through the water, recording data on temperature, salinity, and chemistry. Some carry cameras or small traps to capture life samples. As they fall, sensors record the gradual increase in pressure, 100 atmospheres, 500, 1000, and the steady drop in temperature. When they reach the bottom, they sit silently, waiting. as the weight of the world bears down on them. Days later, they release ballast weights and ascend slowly back to the surface, bringing with them fragments of the deep. The instruments themselves must withstand more stress in a few hours than most materials experience in their entire lifetime. Each successful recovery is a triumph not just of engineering, but of understanding the language of pressure. Down in the crushing stillness, where the trench floor stretches for hundreds of kilometers, the alchemy continues. Life feeds on the chemistry that pressure makes possible. Water and rock react to form hydrogen and methane. Bacteria consume those gases and produce organic molecules. Larger organisms feed on those bacteria. The cycle repeats endlessly. What begins as geological transformation becomes biological energy. In this way, pressure doesn't only shape life, it generates it. The deep ocean is a vast laboratory of slow reactions, where the laws of physics and biology merge into a single system of endurance. When scientists model how life might exist on other worlds, on the icy moons of Jupiter or Saturn, they often look to the Kermadec Trench for clues. The conditions here, darkness, cold and crushing weight, are similar to what might exist beneath the ice-covered oceans of Europa or Enceladus. If life can thrive under pressure on Earth, it might do so elsewhere. The trench becomes a window not just into our own planet, but into the possibilities of life in the universe. The same chemistry that sustains microbes here could sustain them beyond Earth, where sunlight never reaches but water and pressure are abundant. The lessons of Kermadec extend beyond our world. As the exploration lights fade and the submersible begins its ascent, the trench remains unchanged. The pressure continues its steady work, invisible and absolute. It compresses, stabilizes, preserves. It sculpts the landscape, defines the chemistry, and determines what can live. Every creature here is a living equation solved under the weight of the world. They are not fragile miracles. They are inevitabilities, shaped by the physics of existence. The deep doesn't defy nature's laws, it fulfills them. Pressure, in the end, is not an obstacle. It is the ocean's quiet genius, the alchemy that turns force into life and darkness into endurance. Even here, where darkness reigns and pressure seals every motion in silence, the surface never fully disappears. The trench might seem like a world apart, an isolated chasm buried beneath 10 kilometers of ocean, but in truth, it is tied to everything above. The deep remembers what the surface forgets. Every storm, every bloom of plankton, every current that sweeps across the Pacific leaves an imprint that drifts downward in the slow rain of matter that connects the two realms. The Kermadec Trench, for all its remoteness, is a reflection of the surface ocean, a record of its cycles, its chemistry, and its living pulse. It begins with light, as all oceanic stories do. At the surface, sunlight feeds the phytoplankton that form the base of marine life. They capture carbon from the atmosphere and turn it into organic matter. Some of that matter is eaten by zooplankton, some by fish, and some escapes the food web entirely, sinking into the depths as tiny flakes of debris. Over days, months, and years, this continuous drift of microscopic particles, plankton remains, fragments of shells, specks of dust and fecal pellets, forms what scientists call marine snow. It is the ocean's slowest snowfall, a gentle, endless descent that links the living sea above to the hidden one below. In the open Pacific, much of this snow dissolves or is consumed before it can reach the deep. But over the Kermadec Trench, where the seafloor plunges into shadow, the descent becomes more direct. The currents and eddies that swirl along the trench walls funnel organic material downward like invisible rivers. The trench acts as a natural collector, a place where the detritus of the ocean gathers. Each grain of sediment, each layer of silt carries the memory of the surface world, the carbon of once living things, the trace elements of volcanic dust, the chemical fingerprints of climate and current. To an observer, This slow rain would be almost invisible, a faint shimmer in the beam of a submersible's light. Yet it is the deep ocean's primary source of nourishment. Every amphipod, every snailfish, every microbe in the Kermadec abyss depends on it. The energy that sustains them was once sunlight, captured by a microscopic organism far above and passed down, fragment by fragment until it reached the trench. It's an unbroken chain, delicate and precise. The deep doesn't create its own food, it inherits it, slowly and faithfully. The link between surface and abyss isn't only biological, it's chemical. The water that fills the trench once began its journey at the surface, near the poles, where cold air and salt made it dense enough to sink. It has travelled for centuries through the global conveyor of ocean currents, absorbing gases, nutrients, and traces of life along the way. By the time it reaches the Kermadec Trench, it carries with it a record of the world's climate and history, dissolved oxygen, carbon dioxide, nitrogen, and countless other compounds. Scientists can measure these traces and reconstruct the story of the planet's past. The trench, in this sense, is not just a depth, it's an archive, a place where time itself settles out of the water column. But the echoes of the surface are not always gentle. Sometimes they arrive in violent bursts. When a large whale dies and sinks, it becomes a sudden feast, a rare moment of abundance in the deep. The fall of a whale carcass, what researchers call a whale fall, creates an oasis of life that can last for decades. Within days, scavengers strip the flesh. Within months, bacteria begin to break down the remaining bones, releasing sulfur compounds that feed entire microbial ecosystems. Crustaceans, worms, and mollusks move in, each species arriving in sequence, each performing its role in the slow decomposition. Eventually, nothing remains but a patch of enriched sediment, a small echo of the surface life that once swam above. These events are rare, but their impact lasts for centuries. The carbon from a single whale can feed generations of trench organisms, seeding new populations across kilometres of seafloor. The deep ocean stability is built on these rare interruptions, moments when abundance punctuates scarcity. The Kermadec Trench, being one of the deepest collection points in the Pacific, receives more of these gifts than most. Each one is absorbed into its slow economy of decay and renewal. The connection between above and below isn't always biological. Dust from continents and volcanic ash from distant eruptions also find their way here. When volcanoes in Tonga or New Zealand erupt, the fine particles they release can drift across the ocean for weeks before settling into the trench. These particles carry minerals and trace elements that alter the chemistry of the seafloor. Iron, for example, can stimulate microbial growth. Silica and sulfur can change the balance of chemical reactions that sustain life in the sediment. Even the faintest layer of ash becomes part of the deep ecosystem, influencing processes that unfold over millennia. The Kermadec region is particularly active volcanically. Its arc of seamounts constantly exhales minerals and gases into the water. Hydrothermal vents along the trench walls release plumes that rise hundreds of meters, carrying iron, manganese, and other metals that eventually disperse through the deep currents. Some of these particles drift upward, feeding surface plankton blooms thousands of kilometers away. The exchange works both ways. The surface feeds the deep through the fall of organic matter, and the deep feeds the surface through its chemistry. The ocean's circulation turns these two halves into a single system, a planetary metabolism powered by motion, temperature, and time. It's easy to imagine the trench as still, but that's only true when viewed in human time. Over centuries, the deep currents that move through it shift subtly, redistributing oxygen and nutrients. These changes mirror the planet's climate above. When the surface warms or cools, when ice caps grow or shrink, the deep ocean feels it. Not immediately, but eventually. The water that fills the Kermadec Trench today may carry the signature of climate conditions from the Middle Ages. In 1,000 years it will reflect the conditions of our own era. The deep is always listening, always recording the surface's stories, one slow current at a time. This communication between worlds isn't symmetrical. The surface influences the deep far more than the deep influences the surface, at least on short time scales. But the feedback loops are real. When the deep ocean stores carbon, it cools the atmosphere. When that carbon returns through upwelling or volcanic release, it warms it again. The Kermadec Trench, through its immense capacity to store organic carbon in sediment, is part of that balance. The carbon that settles here can remain locked away for tens of thousands of years. Each particle that sinks is a tiny withdrawal from the planet's atmospheric account, a fraction of stability bought through depth. Human researchers have only recently begun to understand how important this role is. The deep trenches, once thought barren and inert, are now recognised as key players in the global carbon cycle. They are the final repositories of the planet's organic matter, the last stop in the ocean's long recycling chain. Without them, carbon would return to the surface more quickly, the atmosphere would grow warmer, and life as we know it would change. The Kermadec Trench, silent and unseen, helps regulate the temperature of the world above. Its stillness is a form of balance. Sometimes echoes from the surface arrive as sound. Hydrophones lowered into the Kermadec depths have captured noises that defy easy classification. Distant earthquakes, volcanic rumbles, the creak of shifting rock, and, faintly, the songs of whales. The sound of a humpback call, distorted by distance and depth, can travel for hundreds of kilometres. It reaches even into the trench, a faint melodic vibration moving through the heavy water. To us, it might be little more than noise, but to the creatures that live here, it's part of the texture of existence. The ocean carries voices through its layers, turning them into vibrations that shape behaviour, orientation, and perhaps even memory. Sound moves differently in the deep. It bends and refracts through layers of varying temperature and pressure, creating channels where it can travel for extraordinary distances. The SOFAR channel, short for sound fixing and ranging, lies between 600 and 1,700 metres deep, and acts as a kind of acoustic highway. Some of the sounds that reach the trench originate in this channel, travelling through it like whispers through stone corridors. The result is a world connected not by sight but by sound, a continuous hum linking surface storms, tectonic shifts, and living voices in one unbroken vibration. When scientists study the isotopic composition of trench sediments, they can trace events that happened far above. A spike in certain isotopes might correspond to a volcanic eruption, a period of drought, or a change in ocean currents. These records, stored grain by grain, provide a history of the surface world written in mud. Each layer is a message, an echo that sank and settled. To read it is to eavesdrop on the conversation between the surface and the abyss. The Kermadec Trench is not just a destination, it's a listening post for the planet's own history. Even life in the crushing dark carries traces of its surface ancestry. Genetic analysis of trench organisms reveals that many species evolved from shallower relatives that slowly adapted to depth. Over generations, as they followed food downward, they acquire the traits necessary to survive: the loss of pigment, the development of pressure-resistant proteins, the reduction of eyes. The deep didn't create them from nothing, it shaped them from what already existed. Every amphipod, every fish, every microbe carries within it the memory of light, a molecular echo of the world it left behind. In recent years, scientists have also found evidence that plastic pollution has joined this conversation between surface and deep. Microplastics, carried by currents and marine snow, have been discovered embedded in Kermadec sediments. They are the newest echoes of human civilization, drifting downward like an unwanted signal. These particles, though small, can affect the chemistry of the sediment and the organisms that ingest them. It's a sobering realization. Even the most remote ecosystems now bear the imprint of human presence. The deep ocean, once thought immune to our reach, has become part of our story, one we've written into every corner of the planet. But even these unwanted echoes remind us of connection. The deep doesn't reject what falls from above, it integrates it. Over time, the plastic will fragment further, mix with organic matter, and become indistinguishable from the sediment. The ocean's patience is infinite. It transforms everything it receives, whether natural or artificial, into part of its slow, steady record. The trench doesn't forget, it absorbs. From time to time, earthquakes shake the trench walls, stirring the sediment and sending plumes of dust rising into the water. These events resuspend centuries of settled matter, briefly reversing the direction of the marine snow. For a while, the deep becomes turbulent, filled with motion and haze, but the disturbance passes and the particles begin to fall again, resuming their slow descent. The process is unending. The surface sends its echoes downward, the deep receives them, and together they maintain the balance of the planet's cycles. In the stillness of the Kermadec depths, every echo eventually becomes part of the whole. A storm at the surface, a bloom of plankton, a volcanic eruption. Each event leaves a trace that drifts down through the dark, fading as it falls until it becomes one with the trench floor. The deep doesn't mirror the surface perfectly. It distills it, stripping away noise and motion until only essence remains. In that sense, the trench is not a graveyard, but a translation, a place where the chaotic energy of the living world is transformed into permanence. Above, the waves keep moving, the wind changes, the sunlight dances across the water in endless patterns. But beneath all of it, the Kermadec Trench continues its patient work, receiving, recording, transforming. The deep and the surface are not opposites. They are halves of a single whole. The life that thrives in the crushing dark is sustained by the memory of light, and the light that nourishes the surface ultimately feeds the deep. Between them lies a thread of continuity that no distance or depth can break. And so, while the trench may seem detached, it is anything but isolated. It is the ocean's quiet listener, its patient archivist, its eternal recorder of surface whispers. Every echo that reaches it, whether of sunlight, storm, or song, finds a place in its depths, where time slows, pressure steadies, and the world above becomes part of something vast and unending. For as long as there have been questions about what lies below, humans have wanted to see it. Curiosity is a kind of buoyancy. It keeps us from sinking into indifference, even when the depths seem unreachable. The ocean has always been both mirror and mystery, its surface familiar, its interior untouchable. For centuries the deep was an abstraction, a void filled with imagination and myth. It was said that no light could reach it, no life could endure it, no human could descend and return. But slowly, through steel and circuitry, we found ways to breathe where no lungs could, to see where no eyes were meant to open. The story of how we came to explore places like the Kermadec Trench is, in a way, a story about our need to make contact with the invisible. The first explorers of the deep were not men in submersibles, but weights, ropes, and lead lines dropped from wooden ships. In the 19th century, mariners began to measure ocean depth by lowering long cables into the water and waiting for them to touch the bottom. The process could take hours, even days, and the results were often uncertain. When those early sailors sounded the Pacific north of New Zealand and found no bottom within the reach of their lines, they knew only that the ocean here was deeper than their instruments could grasp. The Kermadec Trench existed then only as an absence, a space without measure, a question without an answer. By the mid-20th century, technology began to change that. The invention of sonar allowed scientists to map the seafloor using sound instead of line and weight. A pulse of energy was sent downward, and the time it took for the echo to return revealed depth. The results were astonishing. The ocean floor, once thought to be flat and featureless, was revealed as a landscape of mountains, valleys and canyons more dramatic than any on land. The Kermadec Trench appeared on those maps as a narrow ribbon of darkness, plunging deeper than nearly any other known point on Earth. For the first time, it had a form, a visible fold on the invisible surface of the planet. But to measure depth is not to know it. The challenge was not just to see the trench from above, but to enter it. The first humans to descend into the deep ocean did so in vessels that seemed more like experiments than ships. In 1960, Jacques Picard and Don Walsh entered the bathyscaphe Trieste and sank into the Mariana Trench, reaching nearly 11,000 metres. Their cabin was a steel sphere barely large enough for two men to sit side by side, surrounded by gasoline for buoyancy and encased in pressure-resistant metal. The descent took nearly 5 hours. At the bottom they could see only a pale patch of seafloor through a small window, but that moment proved what had once been unthinkable. Humans could visit the deepest places on Earth and return alive. That same principle, spherical design, neutral buoyancy, and balance with pressure, remains the foundation of all deep diving craft. Every submersible, every robotic lander that reaches the Kermadec Trench is a descendant of that idea. Machines built for the deep must be both rigid and fluid, both strong and flexible. They must breathe in a way, exchanging gases, managing energy, maintaining balance. The air inside them is artificial, compressed and recycled through systems that mimic the lungs of living creatures. Pumps and valves act as hearts. Sensors function as nerves. Cameras become eyes that never blink. In the absence of light, these machines see by projection, by shining their own illumination into the dark. They do not simply explore, they translate. When a modern submersible descends toward the Kermadec floor, it enters a realm that no satellite can map in detail and no diver can endure. The water pressure increases steadily, compressing every joint, every seal. The hull must resist forces that would crush concrete, yet remain light enough to maneuver. Engineers design these crafts with redundant systems, multiple layers of protection, backups for every critical component. Each cable, each bolt, is tested to survive thousands of atmospheres of stress. Still, the descent is not without risk. A single flaw, a microscopic imperfection in the weld of a viewing port could mean catastrophic collapse. The pilots who guide these machines understand that risk intimately. Inside the small cabin, the world narrows to a handful of glowing screens, the hum of life support systems and the rhythmic hiss of pumps. Outside, there is only blackness. The descent feels endless, marked only by the ticking numbers of depth. Time stretches. The mind adjusts. The pressure builds until it feels like falling into another state of matter entirely. Hours pass before the first glimpse of the trench floor appears on the monitors. Flat, pale, scattered with silt and small forms that drift in the current. The technology that makes such journeys possible has evolved rapidly. Today's deep-diving submersibles are equipped with robotic arms capable of collecting samples, sensors that measure temperature and salinity, and high-resolution cameras that can capture light at the edge of darkness. Many of them operate autonomously, without a human crew. These remotely operated vehicles, or ROVs, are connected to the surface by cables that transmit power and data. They can stay at depth for days, maneuvering with quiet precision, guided by pilots who sit in control rooms thousands of meters above. The machines become extensions of human perception, our eyes, our hands, our instruments in places our bodies cannot go. One of the most remarkable of these machines is the Hadal Lander, a free-falling platform designed to reach trenches like Kermadec. It carries cameras, lights and sensors enclosed in titanium spheres, descending silently through the water until it settles gently on the seafloor. Once there, it waits. It records the passage of life, the chemistry of the sediment, the motion of the water. Some landers release bait, small pieces of fish or squid, to attract deep-sea animals. Amphipods, snailfish, and other scavengers arrive, drawn by the rare scent of food. The cameras capture their movements, their delicate gestures in the dark. Hours later, the lander releases ballast weights and begins its slow ascent, carrying back its observations from a world that has never known light. Every mission to the trench adds to our understanding, but it also raises new questions. What does it mean to explore a place so far removed from human existence that no sound of civilization can reach it? The machines that breathe for us are not just tools, they are ambassadors, carrying our curiosity into the silence. When they touch the sea floor, they bring with them fragments of the world above, light, noise, movement, electricity. They are, in a sense, the surface made tangible in the deep. Through them, we make contact with something older and more patient than ourselves. Yet every journey is fleeting. The submersibles return, the ROVs are retrieved, the data analysed. The deep remains unchanged. The trench doesn't need us. It only allows us to visit. The information we gather, chemical readings, footage, samples, is valuable not because it alters the deep, but because it alters us. It changes how we think about life, about pressure, about endurance. It shows us that the ocean is not merely a barrier or a resource, but an entire mode of existence beyond our usual senses. The relationship between human and machine in this exploration is intimate. The deep has no air, no room for error, so every system must work flawlessly. Oxygen is scrubbed and recycled. Power is rationed. Cameras must function in near total darkness without overheating. Communication with the surface is delayed, often reduced to short coded signals. The pilot and the machine become one entity, a closed loop of awareness and adjustment. Every noise, every flicker of light, every vibration is registered, interpreted, and responded to. To dive here is to enter a dialogue with both technology and the ocean, each responding in kind to the other's presence. The deeper we go, the more our machines resemble the creatures we find there. Some ROVs are shaped like fish, with fins and tails that move gently through the water. Others glide like rays, their smooth bodies designed to minimize turbulence. Sensors mimic the lateral lines of fish, detecting pressure changes and currents. Artificial intelligence allows them to navigate autonomously, to adjust to the shifting landscape without direct human control. In essence, we have built mechanical organisms, machines that don't simply survive the deep but belong to it in their own mechanical way. These designs aren't purely functional, they're philosophical. To survive in the deep, a machine must adopt the same principles as life itself: flexibility, balance, and patience. It must yield rather than resist. The technology we create to explore the trench mirrors the adaptations of the amphipods and snailfish. It's not about conquering the environment, it's about becoming part of it, even temporarily. The deeper we push our instruments, the more we are forced to imitate the ocean's own logic. The information gathered from the Kermadec region has reshaped science's understanding of the Earth's systems. Sensors have recorded chemical gradients that reveal how carbon and nutrients move through the ocean. Cameras have captured species never seen before, organisms so delicate they vanish at the touch of light. Some of these discoveries have practical implications: new enzymes that function under pressure, potential medical applications, insights into how life might exist elsewhere in the universe. But beyond utility lies something quieter: the recognition that the planet is still largely unexplored, that vast regions remain beyond reach. In recent years, robotic explorers have begun to operate semi-independently, guided not by remote pilots but by algorithms that learn from their surroundings. These autonomous vehicles can descend into trenches like Kermadec, navigate the terrain, and return with data no human has directly witnessed. They act without eyes, without breath, without fear, machines that experience the deep not as alien, but as normal. The more capable these systems become, the closer we approach a strange inversion, machines becoming the primary witnesses of the natural world, while humans watch through their lenses. In the deep, technology doesn't just extend perception, it replaces it. There's a certain irony in this progress. The deeper we reach, the more distance grows between us and what we explore. The first explorers of the deep risk their lives in cramped metal spheres, feeling every groan of the hull. Today, we send machines that can dive deeper, stay longer, endure more. But they do so without sensation, without the human element that made those early descents both terrifying and transformative. We see more than ever before, but we feel it less. The machines breathe for us, but they do not dream for us. Still, without them, the trench would remain a blank space on the map, a silence in our understanding. Each camera that descends into the Kermadec depths illuminates a fragment of the unknown. Each sensor that records pressure and chemistry adds a line to the planet's story. Through technology, we translate the incomprehensible into knowledge, into language. The deep ocean teaches us that seeing is not just a physical act. It's a kind of empathy, a reaching out into what was once unseen. Even the failures matter. Many deep-sea missions end in loss. Equipment crushed, data unretrieved, machines swallowed by the pressure they were built to endure. Somewhere on the trench floor lie the remains of lost probes and cameras, silent monuments to our persistence. They've become part of the ecosystem now, covered in sediment, colonized by microbes, integrated into the same slow cycle as everything else. The ocean accepts them, as it accepts everything that falls into it. What was once technology becomes geology, another echo of the surface woven into the fabric of the deep. For all the sophistication of our tools, the fundamental challenge remains the same, to understand without intrusion. The more we send into the deep, the greater our responsibility to preserve it. Machines that breathe for us must also represent us well. They must measure without harming, observe without altering. The deep sea does not heal from disturbance the way shallow waters do. Each movement of a thruster stirs centuries of settled sediment. Each light beam startles creatures unaccustomed to brightness. Exploration is necessary, but it carries a weight that mirrors the very pressure we study. The cost of knowledge here is gentleness. The engineers who build deep-sea machines often describe them in human terms, as if affection were part of the process. They speak of them as companions, partners, even emissaries. The truth is that each of these machines embodies an act of trust. Trust that the physics will hold, that the systems will work, that the connection to the surface will not break. When the submersible disappears beneath the waves, it takes with it not just equipment, but faith in our ability to coexist with what we don't control. The ocean rewards that faith not with comfort, but with perspective. As the submersible rises again from the trench, its lights fade from view. The data it carries will take months to analyze, the samples years to study. But the journey itself is its own kind of message. The deep does not yield its secrets easily. Each descent is a conversation, each ascent an answer that leads to another question. The machines that breathe for us don't just explore, they remind us of the boundaries we have yet to cross, both physical and intellectual. Above, the surface world continues, ships move, storms form, the sun arcs across the sky, but far below, the machines have already returned to silence. The trench remains, unmoved, unbothered, eternal. It doesn't need us, but it tolerates our curiosity. And through the eyes of our inventions, we continue to learn what it means to reach into the dark, not to conquer it, but simply to see it, to understand that even the most crushing depths are not beyond life or comprehension. They are, in their quiet way, waiting to be known. Even beneath the pressure and silence, the earth never stops moving. The seafloor beneath the Kermadec trench is not a static foundation, but a living system, restless and cyclical. It shifts, bends, and exhales heat from the planet's interior. What feels eternal from above is, down here, a continuous motion stretched across timescales too long for human perception. The crust creaks under tension, faults slip, and magma seeps upward through invisible cracks. It's slow, patient movement, but it never ceases. This deep, ceaseless activity is the planet's hidden pulse, the quiet rhythm that sustains its balance. The Kermadec Trench sits at the frontier of two great tectonic plates, the Pacific and the Australian. They converge here in a slow collision, one sliding beneath the other, forcing the seafloor downward into the mantle. This process, called subduction, is both destruction and renewal at once. It consumes old crust, melts it into magma, and recycles it into new land elsewhere. The motion is constant, just a few centimetres per year, but the forces involved are immense. Over millions of years, that steady convergence has built entire mountain ranges, carved deep trenches, and shaken the ocean itself. The Kermadec system is one of the most active on Earth, a boundary where the energy of the planet reveals itself most clearly. At these depths, the human sense of time breaks down. The movements that shape the trench are measured not in minutes or centuries, but in epochs. Rocks shift like glaciers, flowing slowly under heat and pressure. Fault lines creep for decades before releasing their strain in sudden earthquakes that ripple through the ocean. When they happen, the sound is indescribable. A low, resonant roar that rolls through the water for hundreds of kilometres. The trench becomes, for a few moments, the voice of the planet itself, speaking in vibration and resonance. The surface may never notice more than a faint tremor, but down here, the pulse is overwhelming. The energy that drives this movement comes from deep within the Earth's mantle, a layer of molten and partially solid rock that circulates like slow, convection currents in a pot of water. Heat from radioactive decay and residual energy from the planet's formation causes the mantle to rise and fall, dragging the crust along with it. Where plates collide, trenches form. Where they pull apart, ridges and new seafloor emerge. The Kermadec Trench is part of that global system, a great breathing mechanism that regulates the surface above. Without subduction, there would be no volcanoes, no mountains, no continents as we know them. The planet would be geologically dead, like the Moon or Mars. The very instability of the Earth is what keeps it alive. In the Kermadec region, that vitality is visible even in the unseen. Seismic sensors placed along the trench walls record constant microtremors, small slips and adjustments as the plates grind against each other. These tremors are too faint for humans to feel, but they accumulate into larger events over time. Every few decades, a major earthquake strikes, releasing centuries of stored tension in a single moment. Some of these quakes trigger tsunamis that travel across the Pacific, carrying the trench's energy to distant shores. Others pass quietly, their force absorbed by the sea, but all are part of the same rhythm, the slow contraction and release of a living planet. Hydrothermal vents along the subduction zone provide another expression of that hidden pulse. These are the planet's breath, fissures where seawater seeps into the crust, becomes superheated by magma, and then rises back to the ocean through vents. The water that emerges is rich in minerals, iron, manganese, sulfur, and methane. Around these vents, life clusters in improbable abundance. Bacteria feed on the chemicals, forming the base of ecosystems that include worms, crabs, and other creatures that never see sunlight. In the darkness of the trench walls, these vent communities shimmer faintly, glowing with bioluminescent life. They are miniature worlds powered not by light but by chemistry, living directly from the planet's internal heat. What's remarkable is how stable these systems are despite their volatility. A vent can erupt or collapse without warning, its flow redirected elsewhere, but within weeks life recolonizes it. Microbes drift through the water like seeds in the wind, settling wherever new heat appears. The trench's living inhabitants are tuned to these changes. They sense the planet's pulse not through sight or sound, but through chemical gradients, the faint whiff of hydrogen sulfide, the shift in temperature, the signature of renewal. For them, the planet's heartbeat is not catastrophic. It's the rhythm of existence itself. Scientists studying the Kermadec subduction zone often describe it as one of the most dynamic geological laboratories on Earth. Along its length, volcanoes rise from the seafloor, each one connected to the subducting slab below. Some are dormant for centuries, then suddenly awaken. Others release steady plumes of gas and heat, venting the planet's interior like pressure valves. The islands that form above the trench, Raoul, Curtis, Macaulay, are the visible tips of these volcanic mountains. They are fragile, impermanent creations, built from ash and lava that will one day erode and sink again. The islands are, in essence, the exhalations of the deep, fleeting evidence of the slow respiration of the Earth. Each eruption in this chain adds to the geological conversation between the surface and the abyss. Ash clouds rise into the sky, changing the chemistry of the atmosphere. Lava flows into the ocean, creating new rock. Over thousands of years, these processes recycle entire landscapes. The Kermadec Arc, with its string of volcanoes, is like a diagram of the Earth's internal dialogue, a looping feedback between heat and water, pressure and release. Every tremor, every plume, every eruption is a word in that language, one that speaks through time rather than sound. Even the sediment that settles at the trench floor carries the signature of these movements. Layers of fine volcanic ash alternate with the organic remains of marine snow. Each band marks an event, a storm, an eruption, a climate shift. When scientists extract cores from the trench floor, they are reading a continuous record of the planet's pulse. The data reveals patterns that stretch back millions of years, cycles of calm and upheaval, of rising and sinking. It's a geological heartbeat, one that has never stopped since the ocean formed. If the deep ocean feels timeless, it's only because its time moves too slowly for us to perceive. The Kermadec Trench is not a static chasm. It's a process, a shape formed by the tension between creation and destruction. The same forces that drag the Pacific plate downward also melt it, generating magma that eventually rises again through volcanoes. It's a closed loop of energy, a recycling system that maintains the Earth's balance. The trench is where the planet ingests itself, renewing its crust, regulating its temperature, and maintaining its internal flow. In a way, it functions like a giant organ, one whose steady rhythm sustains the life of the planet without ever being seen. Every once in a while, instruments record something extraordinary. A deep, low-frequency sound called a seismic hum. It's not caused by earthquakes, but by the constant motion of the ocean, an atmosphere pressing against the sea floor. This hum is continuous, measurable everywhere on Earth. It's the background vibration of a living planet, the sound of tides and wind translated through rock. The Kermadec Trench, because of its depth and sensitivity, records this hum more clearly than most places. Scientists listening to it describe it as the heartbeat of the world, a signal that never stops. Even when everything seems still, the planet is murmuring beneath us. The chemistry of the trench floor also reflects this internal motion. Fluids released from the descending Pacific plate rise through the sediments, carrying heat and dissolved elements. They alter the composition of the overlying water, introducing trace metals and gases. These chemical exchanges influence not just local ecosystems, but the global ocean as well. Over geologic time, the trench acts as both sink and source, absorbing material from the surface and releasing it back in transformed form. It's another expression of the planet's cyclical nature. Nothing here is wasted. Everything is exchanged. To understand how deeply connected this process is to life, consider that without subduction, the carbon cycle itself would fail. When oceanic crust sinks into the mantle, it carries with it carbon trapped in limestone and organic sediments. This carbon is then re-released through volcanic eruptions, completing a cycle that regulates the planet's atmosphere. The Kermadec Trench is part of that loop. It is, quite literally, one of the places where the Earth breathes, drawing in and exhaling the gases that make the surface habitable. The quiet pulse that moves the plates also sustains the air we breathe. The technology we use to study these movements is delicate compared to the scale of what it measures. Seismometers anchored to the seafloor detect vibrations with astonishing sensitivity, capturing even the faint tremors caused by distant storms. Pressure sensors measure the rise and fall of tides with millimeter precision. Autonomous underwater vehicles glide along the trench walls, mapping the contours of the subduction zone. From the data they gather, scientists can reconstruct the slow choreography of the planet's crust, its expansions, its fractures, its hidden motion. Yet even with all this knowledge, what they uncover most is humility. The scale of these forces defies our sense of proportion. The trench reminds us that the Earth is not solid beneath our feet. It's alive, restless, and in constant negotiation with itself. Sometimes, the trench's pulse quickens. In 2016, a powerful earthquake struck the region, one of the largest ever recorded in the Kermadec system. The seafloor shifted by several meters, releasing energy built up over centuries. The tremor sent ripples through the ocean, altering currents, stirring sediments, and subtly changing the shape of the trench itself. For a brief time, the deep world shuddered, but then, as always, it returned to stillness. The planet's pulse is not steady like a heartbeat. It's irregular, marked by long silences punctuated by sudden bursts of motion. It's a rhythm written in rock rather than flesh. Even in apparent stillness, heat seeps upward. The mantle below the trench reaches temperatures of over 1,000 degrees Celsius. Though the water above remains near freezing, just beneath the crust lies a sea of molten rock. The boundary between them is astonishingly thin. Only a few kilometers of solid material separate the coldest part of the planet from one of its hottest. That fragile balance defines the character of the deep ocean, the creatures that live here, the chemistry that sustains them, even the pressure that holds everything together, all are shaped by the interplay of these extremes. The trench, in its quiet way, is a negotiation between fire and ice. When we talk about the pulse of the planet, we usually mean something metaphorical, but here it's literal. The seismic activity, the heat flow, the slow migration of tectonic plates, all of it is measurable. The Earth's energy moves like blood through its crust, carried by convection currents and expressed through earthquakes and volcanoes. The Kermadec Trench is one of the main arteries in that system, channeling motion from the mantle to the surface. The pressure we study in the deep is not just physical, it's dynamic, a manifestation of energy and perpetual motion. The longer we observe this hidden pulse, the more it becomes clear that the deep ocean is not a passive environment. It participates in the planet's metabolism. Every tremor releases minerals into the sea. Every shift in the crust changes the flow of nutrients. The ocean and the Earth's interior exchange information constantly, each responding to the other's movements. In the Kermadec region, that dialogue is especially strong. It's one of the few places on the planet where the boundary between geology and biology is thin enough to see through. Life grows directly from heat and rock. The pulse that shakes the trench also sustains the living world. In the end, what the Kermadec Trench reveals is not just the planet's power, but its coherence. The Earth is not a collection of separate systems. It's a single, continuous process of motion, chemistry, and adaptation. The same forces that fold mountains and open trenches also guide the currents, shape the climate, and sustain the ocean's life. The pulse that moves beneath our feet is the same one that moves within us, though we feel it in different forms. Down here in the deepest places, that truth is unmistakable. The planet breathes and the ocean listens. Together they keep time, slowly, endlessly in the dark. The seafloor looks still, but it isn't. What appears to be a plain of dust and sediment, soft and unchanging, is actually a living archive, a slow-moving library written in the language of particles. Every grain that settles here carries a message from above, a fragment of plankton, a fleck of volcanic ash, a trace of metal or carbon. The Kermadec Trench is one of the deepest, most remote repositories of this material on the planet, and its mud records the quiet conversation between ocean, atmosphere and Earth over millions of years. To study it is to read the planet's diary, though the handwriting is delicate and the sentences span epochs. Each layer of sediment tells a story about a different time. The uppermost few centimetres might record only the last century or two, while deeper layers preserve signals from ancient climates, mass extinctions and planetary transitions. The process is slow but relentless. Every day new particles fall from the surface, microscopic skeletons of diatoms and foraminifera, soot from distant fires, fragments of dead plankton, mineral dust carried by the wind from continents thousands of kilometres away. These tiny remains drift downward for weeks or months, eventually joining the seafloor where they are compacted, layer upon layer, into a continuous record of change. The mud is not uniform. It's a complex mixture of organic and inorganic matter, each part shaped by different forces. The volcanic activity of the Kermadec Arc adds ash and minerals, while biological productivity at the surface contributes organic carbon. Over time, chemical reactions between these components create new minerals, clays, sulfides, carbonates, that lock in the history of the water above. The result is a stratified memory, one that scientists can read using tools far more sensitive than eyes. When cores are extracted from the trench, they come up as long cylinders of compressed sediment, often meters in length. At first glance they appear simple, just shades of brown, grey and black, but under microscopes and spectrometers they reveal astonishing detail. Variations in colour mark changes in oxygen levels, iron content or biological activity. Tiny shells embedded within the mud can be dated and analysed for isotopic composition, providing clues about the temperature and chemistry of the ancient ocean. Even the ratio of certain elements like calcium to magnesium can indicate how the climate shifted between ice ages and warm periods. In this way, the trench's mud functions like a global climate archive, recording fluctuations in carbon, temperature and life across unimaginable timescales. To read these messages, scientists use techniques that border on forensic. They measure the decay of radioactive isotopes like carbon-14 and uranium-thorium to date layers precisely. They analyse fossilised microorganisms to reconstruct ecosystems that disappeared millions of years ago. Some even examine the orientation of magnetic minerals to track reversals in the Earth's magnetic field. Each sample adds a line to the story, connecting the present trench to a past ocean that may have looked entirely different. The Kermadec sediments contain traces of everything that has ever passed through this part of the Pacific. Volcanic eruptions, plankton blooms, even human activity from the surface. It's humbling to realise how sensitive this system is. A single change in temperature or current at the surface can alter the rate at which particles fall, the type of organisms that thrive, or the chemistry of the sediment below. The deep ocean might feel timeless, but its mud keeps precise time. Every layer is a timestamp, a fingerprint of the planet's shifting equilibrium. And because the trench is so deep, so undisturbed, its record is unusually complete. Unlike shallower seafloors that are churned by currents and storms, the Kermadec Trench preserves even the finest details, untouched for millennia. The deeper one looks into these sediments, the further back the story stretches. Some layers date to when the Pacific Plate first began to sink beneath the Australian Plate, forming the trench itself. Others capture the imprint of glacial cycles, the slow breathing of the planet as ice advanced and retreated across continents. During ice ages, dust from dry lands drifted farther across the ocean, leaving distinctive mineral signatures in the mud, During warmer interglacial periods, plankton thrived at the surface, and the sediments became richer in organic carbon. These cycles repeat like verses in a poem written by the Earth's climate. What's most remarkable is that even microscopic organisms leave their voices in this archive. Foraminifera, those tiny single-celled creatures that build intricate shells, serve as one of the most valuable recorders of ancient ocean conditions. When they die, their shells sink and become part of the sediment. The ratio of oxygen isotopes in those shells reflects the temperature and salinity of the water in which they lived. By analysing thousands of them from different layers, scientists can reconstruct a timeline of ocean temperature spanning hundreds of thousands of years. In the Kermadec Trench, where sediment accumulates slowly but continuously, these timelines reach back to the origins of the modern Pacific circulation system. Sometimes the mud reveals abrupt changes, thin bands of distinct composition that mark catastrophic events. A layer of coarse volcanic ash might indicate a massive eruption from one of the Kermadec volcanoes. A sudden spike in iridium could signal a meteor impact. A dark, organic-rich stratum might record an ancient episode of ocean anoxia, when vast regions of water lost their oxygen and life briefly suffocated. These are the punctuation marks in the planet's long sentence, brief but defining. Each one corresponds to a moment when the Earth's systems faltered and then recovered, a reminder that stability has always been temporary. More recent layers contain subtler, yet equally telling, signals of human influence. Industrial pollutants, microplastics, and artificial radionuclides have begun to appear even in the deepest sediments. These compounds travel through the atmosphere and ocean currents, eventually settling in the same mud that records natural history. The line between human time and geological time is vanishing. Future scientists, if they still exist to study these layers, will find a sharp boundary, one that marks the beginning of our era. It will be identifiable by the sudden appearance of synthetic materials, isotopes from nuclear tests, and a spike in carbon deposition from fossil fuel combustion. In that sense, humanity has already written itself into the planet's stratigraphy. Our actions are now part of the trench's memory. When viewed from this perspective, the Kermadec mud is not just an accumulation of debris. It's a kind of consciousness, a physical memory of everything that has happened to the Pacific and beyond. The weight of water above compresses it slowly, but it never forgets. The messages encoded within it can outlast civilizations, species, even continents. They will remain legible long after the ocean's surface has changed shape and the land we know has drifted elsewhere. The deep ocean is often described as timeless, but perhaps it's more accurate to say that it's time-rich. Every particle that falls here adds another second to the planet's enduring narrative. The chemical processes that occur within these sediments are as intricate as the stories they contain. Organic material buried in the mud decomposes slowly, releasing methane and carbon dioxide. Sulfate-reducing bacteria consume some of these gases, producing hydrogen sulfide. This in turn reacts with iron to form black iron sulfide minerals, which give certain layers their dark colour. These reactions unfold over centuries, sometimes millennia, transforming soft mud into solid rock. The result is a geological palimpsest, a document rewritten over and over by chemistry but never fully erased. Every once in a while, an earthquake disturbs the trench floor, stirring the sediment and creating turbidite layers, bands of coarser material deposited when the seafloor briefly becomes fluid and flows downslope. These events act like page breaks in the record, marking times of sudden motion. Between them, the slow rain of particles continues, uninterrupted. It's as if the trench alternates between silence and movement, between steady inscription and abrupt revision. The pattern is both predictable and chaotic, a reflection of the dual nature of the planet itself. In some layers, scientists find fossilized traces of bacteria, tiny filaments preserved in minerals. These microbial communities lived and died within the mud, their metabolic activity influencing the chemistry of the surrounding material. Even in death, they leave messages of life, subtle changes in isotopic ratios, distinctive mineral formations, and complex organic molecules that can persist for millions of years. The deep biosphere, the realm of life buried beneath the seafloor, may extend hundreds of meters into the sediment. It's estimated that the total mass of this buried life rivals that of all surface organisms combined. In the Kermadec Trench, that hidden world continues to work quietly, turning chemical gradients into energy, writing its existence molecule by molecule into the archive. The idea that the Earth's history could be contained in mud feels almost paradoxical. We're used to thinking of stone as permanent and mud as fleeting. But in the deep ocean, mud becomes the medium of immortality. The absence of light, the lack of disturbance, the constant pressure, all these factors preserve rather than destroy. The trench floor is less like a graveyard and more like a vault, storing everything that falls into it. From the shells of microscopic life to the residues of human industry, every trace is held in suspension, waiting for someone to interpret it. For researchers, studying these sediments is both an act of discovery and patience. Extracting a core from the trench requires precision. The equipment must descend 10 kilometers through cold, dense water, remain stable on uneven terrain, and then return without contamination. Each mission is a logistical and engineering challenge, but the reward is profound. When the core reaches the surface, it carries with it not just material, but time itself, compressed, layered, and tangible. The scientists who open these cores often describe a sense of reverence, as though they're handling something alive. They read the layers slowly, knowing that each millimeter represents centuries of accumulation. In laboratories, the samples are sliced, scanned, and analysed in ways that seem almost ritualistic. Microscopes reveal the skeletal remains of plankton in crystalline detail. Mass spectrometers measure the elemental composition of individual grains. Computer models reconstruct the ocean currents that carried them. Through this process, the mud becomes narrative. Its chemistry turns into chronology, its structure into story. The Kermadec sediments speak not in words, but in ratios, colours, and densities. Decoding them is like listening to the planet whisper through numbers. But even with all our tools, there are limits to what can be known. Some messages are too faint, too complex, or too ancient to interpret fully. The record is not complete. It's partial, fragmented by erosion and compression. Yet, even in its gaps, meaning persists. The very act of recording, of catching even a fraction of the surface world's residue, is enough to remind us of continuity. The ocean never stops documenting its own existence. Every molecule of mud is a record of transformation, a testimony that nothing truly disappears. If the deep ocean has a memory, the Kermadec Trench is one of its most articulate expressions. It listens to the planet's movements, its climate, its biology, and even its mistakes. It writes without intention, without bias, and without end. The messages it keeps are not for us, yet we find ourselves drawn to read them anyway. Perhaps it's because, beneath all our technology and curiosity, we recognise something familiar in that process, the instinct to preserve, to remember, to leave a trace. Somewhere, beneath layers of sediment thicker than any mountain is tall, a new particle is settling. It might be a grain of volcanic glass, a fragment of plankton shell, or a microscopic piece of plastic drifting from the surface. It will come to rest among millions of others, indistinguishable yet essential. Over time it will compact, fossilise, and become part of the planet's archive. Long after we're gone, its presence will remain. Another quiet message in the mud, another sentence in the story the Earth writes about itself, patiently, endlessly, in the dark. The deeper we travel into the Kermadec Trench, the clearer it becomes that fragility and endurance are not opposites here. They coexist in every form, every movement, every flicker of light that breaks the dark. This world is filled with contradictions that somehow balance. Creatures so soft they could be crushed by a fingertip on the surface, yet strong enough to survive under pressures that would destroy steel. The trench is full of giants that move like ghosts and small, glowing organisms that carry entire ecosystems on their fragile chemistry. Down here, strength is measured not by force but by persistence, by the ability to keep living when the world above would call it impossible. It begins with the largest and quietest residents of the deep, the great deep-sea jellyfish, translucent bodies drifting through the water column like living parachutes. Their bells pulse gently, not with speed but with rhythm, conserving energy as they travel through the vertical expanse. They're almost invisible, their tissues filled with water so that their density matches the ocean around them. Some of these jellyfish span meters in diameter, their tentacles trailing into darkness beyond the reach of light. They are fragile giants, creatures without bones, without defences, whose survival depends entirely on their invisibility and stillness. Each pulse of their bell propels them forward just enough to remain suspended between sinking and rising, an endless slow dance with gravity. Other giants hide within the mud. The deep-sea holothurians, sea cucumbers, cover the trench floor, feeding on the thin layer of organic material that settles there. They move slowly, processing the sediment through their bodies, recycling it grain by grain. Each one consumes its own weight in mud every few days, turning death and decay back into nourishment for others. In this way, they keep the cycle of life in motion even at the bottom of the world. They are unremarkable in appearance, soft-bodied and almost shapeless, but collectively they form one of the largest living biomasses on the planet. Without them, the ocean floor would choke on its own remains. Among these slow grazers, there are rarer visitors. Occasionally the remains of a whale or shark descend into the trench, a mass of flesh and bone falling through the water like a star extinguished. When it lands, it becomes the centre of a small world. Amphipods, worms and snailfish converge from all directions, drawn by the scent of decay. Within days the carcass is alive with motion. Crustaceans strip the flesh, bacteria bloom in the marrow, and eel-pout fish circle in the shadows. Over months the skeleton becomes a reef of sorts, covered in mats of sulphur-eating bacteria that glow faintly in the dark. The whale's death becomes an act of creation, sustaining life in a place that has almost none to spare. What's remarkable is how delicate this balance is. Every bit of energy that enters the trench, whether as falling debris or chemical flux, is used and reused until nothing remains. The deep ocean has no waste. Even the smallest flicker of light, the brief spark of bioluminescence from a drifting plankton, marks a transfer of energy, a moment when one form of life reaches another. These flashes might seem decorative to us, but they are messages, defences, lures, and sometimes acts of deception. In a world without sunlight, light itself becomes the most valuable resource of all. The bioluminescent creatures of the Kermadec depths are as varied as they are mysterious. Some produce light to attract prey, others use it to confuse predators. Certain jellyfish release clouds of glowing particles when threatened, dazzling the darkness like underwater fireworks. Small crustaceans flash rhythmically, communicating through sequences of pulses that scientists are only beginning to interpret. Many of these lights are blue or green, the wavelengths that travel farthest through seawater, but others shine in soft reds and violets, invisible to most species but crucial to those that can see them. Every glow carries meaning, every pattern a signal in the language of survival. The chemistry behind these displays is a marvel of efficiency. The light is produced through a reaction between a molecule called luciferin and an enzyme called luciferase with oxygen as the catalyst. The result is cold light, bioluminescence that emits no heat and wastes no energy. In the deep, where food is scarce and every molecule matters, such efficiency is essential. Some organisms host symbiotic bacteria that produce light for them, while others synthesize it themselves. The patterns and colours vary by species, by depth, even by moment. It's not a static trait. It's communication in motion, a form of art written in survival. Watching this light from a submersible is disorienting. It doesn't behave like light on the surface. It doesn't radiate outward to illuminate space. It appears and disappears like breathing. A pulse of blue drifts by, fades, then reappears in another direction. Sometimes it's impossible to tell whether the light belongs to a single organism or a colony of many. In one moment the darkness seems empty. In the next it is filled with flickering constellations. It's like watching thought itself move through water. Fleeting, purposeful, impossible to grasp. Among the most haunting of these lights are the ones that belong to predators. The anglerfish, though rare at these depths, embodies this strange duality of fragility and power. Its body is small and soft, but it carries a luminous lure that dangles from its forehead, a bacterial lantern used to attract prey. In the stillness of the trench, that faint glow is irresistible to smaller fish, which approach thinking it's food. By the time they realise their mistake, the anglerfish has already swallowed them. It's a brutal elegance, a predation built entirely on deception, and yet it fits perfectly within the deep's logic. Energy must move, and everything that exists must find a way to participate in that movement. Other creatures use light to blend in rather than to hunt. Some squid, for example, have photophores on their undersides that emit light matching the faint glow from the surface above. To predators looking upward, the squid silhouette disappears. This counter-illumination is camouflage by mimicry, a biological illusion that turns visibility into invisibility. In the trench, where the direction of light is meaningless, such adaptation is extraordinary. It shows that even here, in a place with no day or night, life finds ways to manipulate perception. But not all light here comes from biology. Sometimes, faint glimmers appear in the sediment, reflections from fragments of glass or metal, remnants of human presence carried down by the slow rain of debris. These are the artifacts of our surface world, microscopic shards from shipwrecks, specks of plastic, grains of industrial ash. Under the submersible's lamps they sparkle briefly, then vanish again into darkness. They are the unintentional bioluminescence of civilization, echoes of our activity scattered across the seafloor. It's unsettling and oddly poetic to think that our waste now mingles with the natural light of the deep, our signals blending with the ocean's own. The fragile balance of this ecosystem depends on isolation. Down here, energy arrives slowly, unpredictably. The creatures that live in the trench are adapted to scarcity, not abundance. A sudden disturbance, a bright light, a burst of noise, a plume of sediment can throw that balance off for years. This is why scientists exploring the Kermadec depths proceed with such caution. Each descent must minimize disruption. Lights are dimmed, engines throttled to silence. Cameras are designed to capture with minimal illumination. The goal is always to witness without interference, to observe the glow without extinguishing it. When researchers first recorded bioluminescence in the Kermadec Trench, they described it as a storm of light in slow motion. The footage showed countless organisms drifting past the cameras, each emitting brief flashes that together formed an unending organic choreography. Some lights flickered like distant lightning, others pulsed rhythmically, as though synced to an unseen rhythm. The scientists noted how few of these species had ever been observed before. Many had no known classification. Their forms defied existing taxonomies. Their lights followed no predictable pattern. It was as if the trench had evolved an entirely separate visual language, one we have only begun to interpret. Even at these depths, fragility is not weakness. It's precision. The bodies of deep-sea creatures are fine-tuned to their environment, adapted to the exact pressure, temperature and chemistry that define their world. A change of even a few degrees, a shift in acidity, could unravel that balance. This vulnerability is what makes the deep ocean both resilient and at risk. It has survived uncountable millennia of planetary change, yet it may not withstand the pace of human transformation. Rising temperatures, plastic pollution, and carbon absorption are slowly altering even the deepest waters. The light still flickers, but it does so in a world that is subtly changing beneath it. There's a strange irony in how the most delicate forms of life are often the most enduring. The jellyfish, soft and ephemeral, has outlived entire lineages of armoured creatures. The bioluminescent plankton, invisible to the naked eye, shapes the behaviour of animals kilometres larger than itself. Even the microbial films that shimmer on the trench floor have persisted since before multicellular life evolved. Fragility, it seems, is not the opposite of survival, but its secret instrument. In the deep, the soft endure while the rigid shatter. The faint lights outlast the bright ones. In this world of slow motion and soft luminescence, even silence feels alive. The flickers of light are not just signals, they're expressions of rhythm, of synchronization between organisms that never meet but share the same space. Some researchers believe that bioluminescence in the deep sea could serve as a kind of ecosystem-wide communication, a network of visual cues that maintains balance. Each light may inform others about movement, abundance, or danger. It's a theory still unproven, but compelling. The idea that the deep ocean's peace is maintained not by isolation, but by constant luminous conversation. Every so often, the submersible lights catch something large moving in the distance, a shadow that drifts through the beams and vanishes again. These encounters are brief, but unforgettable. Sometimes it's a giant amphipod, sometimes a massive jellyfish or a rarely seen deep-sea shark. Their size is startling, their motion slow and deliberate. They are reminders that even in this realm of scarcity, life can grow immense. Yet these giants are fragile too. Their bodies are built for pressure and darkness. Exposure to light or rapid ascent can kill them instantly. The ocean's largest beings are often the most vulnerable to its gentlest disturbances. And then there are the smallest lights, microbial glows so faint they barely register to our instruments. These are the deep's quietest voices, flickering just above the sediment where life begins and ends. Their glow is not meant to attract or defend. It's a byproduct of metabolism, a trace of energy released in chemical reactions. When magnified, these glows look like stars scattered across a dark sky. They are countless and constant, illuminating nothing but themselves, yet collectively shaping the chemical environment of the trench. From a distance, the trench appears as absolute darkness, but within that darkness, everything shimmers faintly. Every creature, every grain of sediment reflects or emits light in some form. The deep is not empty, it's dimly, delicately alive. It's an ecosystem defined by restraint, where even the act of glowing is measured, purposeful, and brief. To witness it is to understand that beauty does not need brightness, it needs only persistence. In the Kermadec trench, fragility and light are inseparable. The jellyfish that drifts, the amphipod that feeds, the microbe that glows, all exist within a balance that depends on stillness and precision. The ocean's giants are soft not because they are weak, but because they've learned the art of yielding. The flickers of light that punctuate the dark are not exceptions. They are the rule, the quiet language of a world that survives through patience. If you could hover there long enough between the slow-moving giants and the clouds of tiny glowing plankton, you might notice how everything is connected by these subtle exchanges. Light passes to light, energy to energy, moment to moment. The trench, for all its stillness, hums with continuity. Every pulse of light, every fragile gesture is part of the same vast persistence that has carried life through ages of change. The flickers come and go, but the rhythm remains, the faint, eternal heartbeat of the deep. At the very bottom of the Kermadec Trench, there is a kind of stillness that doesn't exist anywhere else on Earth. It is not silence, not exactly, because the ocean is never completely quiet. It hums with low vibrations, faint and continuous, the slow speech of water pressing against itself. It is not emptiness either, because even here, in this cold blackness, life continues to move, feed, and grow. The stillness is something different, something more complete. It is the absence of haste. It is the world functioning at the lowest possible energy, everything slowed to the point where change becomes almost imperceptible. It is the planet's resting state, its pulse reduced to a whisper, but still beating. If you could sink here and stop moving entirely, you would feel that quiet in your body long before you saw it. The weight of the water would become constant, no longer an external force but a steady pressure that defines your shape. The darkness would stop being an obstacle and start being a presence, a kind of material in itself. Time would feel stretched, not because it has slowed, but because your senses have nothing left to measure it against. The trench has its own time, dictated by processes too slow for human thought to follow. Everything here, chemical reaction, biological response, geological motion, exists in that deep rhythm. This part of the ocean floor is covered in fine sediment, as smooth as smoke and just as delicate. Every movement of current or creature leaves a trace, a swirl, a line, a ripple that lasts for years before settling again. The submersible lights reveal a surface that looks untouched, but even here the signs of life are everywhere if you know how to see them. Small burrows, trails of amphipods, faint depressions where sea cucumbers are fed. The trench floor is not static. It is always being written upon and rewritten. It's an enormous living page, recording not in words but emotions too slow to notice in real time. Every now and then, a particle falls, a flake of marine snow, a fragment of shell, a thread of organic carbon. It lands softly, joins the others, and begins its long transformation into sediment. Each of these particles began somewhere else, in the upper ocean, in a river that met the sea, in the air that carried dust across continents. They have travelled the full span of the Earth's systems to end here. The trench is where the world gathers itself, where what drifts eventually finds rest. That quiet accumulation is its form of memory. It remembers not by choice, but by inevitability. There are no sharp boundaries here, only gradients. The light from above is gone entirely, absorbed long before it could reach this depth. The temperature is steady, just above freezing. The water holds oxygen, but only barely. Pressure defines everything. It compresses, stabilizes, and preserves. It holds the world in equilibrium. The organisms that live here seem to move outside of time. The amphipods glide over the sediment. Snailfish drift through invisible currents. Microbes in the mud divide at intervals so long they seem eternal. There is no rush, no chase. The pace of life here feels like the earth thinking, unhurried and continuous. This stillness is not lifelessness. It's what allows life to persist. In the absence of sunlight, in the crushing pressure, in the cold that should stop all motion, the deep has found a way to maintain activity just above zero. The chemical reactions that power cells proceed slowly but steadily. Energy circulates through invisible channels. Matter changes form, decays, reforms. Nothing wastes, nothing hurries. The trench is efficient in a way that human systems rarely are. It turns scarcity into stability, making balance out of limitation. The cameras that descend here can record for only a few hours before they must return to the surface. But the world they capture doesn't need to reset when the machines leave. It continues exactly as before, indifferent to being observed. A snailfish flicks its tail and vanishes into shadow. A cloud of sediment drifts upward, then settles again. A single amphipod carries a grain of food twice its size, moving with deliberate patience. There is no sound but the faint hum of the equipment, and then even that fades as the instruments power down. The trench remains complete in its silence. What's striking about the stillness at this depth is how total it feels, even though everything is still moving. The currents here are weak, but they never stop. They carry nutrients and particles slowly along the trench axis, guided by differences in temperature and salinity that change only over centuries. These slow motions are what connect the deepest point to the rest of the ocean. Even here, at the bottom of the Pacific, the trench is part of a system. Its quiet is not isolation, but balance. It's the part of the planet where motion reaches its most stable form, where the endless movement of water, heat, and matter converges into a kind of equilibrium. It's difficult for the human mind to comprehend such scales. We measure time in hours and years, but here, a single layer of sediment might represent 1,000 lifetimes. The amphipod scurrying across the seafloor today is part of a lineage that has changed almost not at all in tens of millions of years. The bacteria metabolizing minerals in the mud are direct descendants of the planet's earliest life. The trench does not evolve quickly. It doesn't need to. In a world defined by patience, longevity becomes the ultimate adaptation. The stillness also hides power. The same tectonic forces that shape mountains and trigger earthquakes are alive beneath this calm surface. The Pacific plate continues its descent, sliding deeper into the mantle, carrying water and rock into the planet's interior. Occasionally a tremor ripples through the trench, stirring the sediment, reminding the deep that motion never fully ceases. These pulses are the planet's slow heartbeat, too long for us to hear directly but always present. Even the stillness depends on movement. It's the surface appearance of balance built on constant internal change. For the organisms that live here, the distinction between stillness and motion doesn't exist the way it does for us. To them, the background conditions of pressure and cold are not barriers, they are constants. The snailfish gliding through the dark does not feel burdened by the weight of the water. It moves as easily here as a bird through the air. The amphipod does not perceive the sediment as desolation, it perceives it as landscape. The microbes that thrive in the mud do not notice the absence of light. For them, chemical energy is illumination enough. Life adapts so completely to its environment that it becomes inseparable from it. The deep stillness is not something life endures, it's what it belongs to. For all our technology, we can only observe the deep in fragments. Our instruments measure, record and return, but we never see it in its total state. What happens between those moments, the days, months and years when no human eye looks, is the true rhythm of the place. It's the slow turning of cycles, the long chemistry of life continuing unnoticed. Each measurement we take is a brief interruption in that ongoing continuity. When the lights turn off, when the cables retract, when the data stops flowing, the deep continues as it always has. It needs no audience, no validation. The stillness of the trench invites comparison to sleep, though even that isn't quite right. Sleep implies rest after activity, a pause before renewal. The trench's stillness is something else, an equilibrium without beginning or end. It is motion reduced to its simplest form. To witness it is to understand that life doesn't always require motion or growth. Sometimes it requires only persistence. The deep has perfected that art. It survives not by competing, but by existing exactly as much as necessary, no more. When researchers speak of the trench, they often do so in practical terms: depth, pressure, chemistry, biodiversity. But beneath those measurements lies something subtler, something that can't be plotted on a chart. The stillness at the bottom of the world carries a kind of presence that defies analysis. It feels ancient, indifferent, complete. It's the stillness of the planet thinking at its own pace, unconcerned with what happens on its surface. Down here, there are no boundaries between elements, no divisions between living and non-living, no separation between past and present. Everything exists in continuity. The light from a submersible fades faster than you'd expect. It doesn't vanish sharply. It's absorbed gradually, like warmth leaving a body. In its wake, the trench returns to its own illumination, faint bioluminescent specks drifting through the dark. They flicker briefly, then disappear. This cycle never ends. The darkness is not absence. It's the medium in which everything happens. Even when there is no visible light, there are always chemical reactions, molecular exchanges, the quiet persistence of matter turning over itself. The ocean, even at its stillest, is alive in every atom. Above this place, the Pacific stretches for thousands of kilometers, full of storms and sunlight and movement. Ships cross its surface, birds rest on its waves, islands rise from its volcanic edges. None of that commotion reaches here. The deep is insulated from the noise of weather, from the turbulence of human life. But it's not separate. The particles falling from the surface, the heat rising from below, the gravity that binds both, all meet here. The trench is not the end of the world, but its meeting point, where everything that moves eventually comes to rest, if only for a while. If there is wisdom in the deep, it lies in that continuity. The stillness here is not peace in the sense of quiet, it's peace as equilibrium. Every motion above, every fluctuation in temperature or current, finds its resolution in this depth. The planet's cycles of destruction and renewal are all absorbed into this one steady rhythm. It's a reminder that endings and beginnings are the same process viewed from different speeds. What falls eventually becomes foundation. What dies becomes nourishment. What disappears becomes part of the next layer. When the instruments ascend again and the lights vanish into the distance, the trench remains unchanged. The amphipods return to their scavenging. The snailfish continue their slow drift. The sediment resettles. Time resumes its long, quiet procession. Above, the ocean returns to its patterns of wind and wave, unaware of what lies beneath. The link between the two worlds is invisible but constant. The deep holds the memory of everything that falls from above, and the surface moves on, unaware that its story is being preserved grain by grain in the mud below. The stillness at the bottom of the world is not something that can be captured in images or described in full. It exists in the space between what we can measure and what we can feel. It's the texture of continuity itself, the realization that everything, no matter how far apart or how slow, belongs to the same process. To sit in that stillness, even in imagination, is to glimpse the world without urgency, without division, without the noise of interpretation. It is the planet breathing in, holding, and never quite exhaling. And somewhere in that quiet, amid the faint glimmer of drifting plankton and the slow pulse of pressure and heat, there is a kind of truth that feels almost human in its familiarity. The deep ocean doesn't strive or despair, it simply continues. It changes at the only pace that guarantees endurance. It listens to everything that falls into it, remembers everything it receives, and gives nothing back except the assurance that the world keeps moving, even when we can't see it. If you could hear the sound of that stillness, it wouldn't be silence. It would be the lowest note imaginable, too long and slow for our senses to register. The sound of a planet at rest within itself. The Kermadec Trench is that note made physical, a resonance that carries through the crust and the water and the air above it, holding everything in balance. It is the Earth's reminder that quiet doesn't mean absence, and stillness doesn't mean death. It means continuity, patience, and the kind of calm that only a living world can sustain. And as we rise back toward the surface, toward a light and sound and movement, that stillness remains below, unchanged, undisturbed, waiting in the dark. The pressure holds, the sediments settle, the faint lights flicker and fade. The trench breathes in its slow way, carrying the planet's oldest rhythm forward. Everything that was, everything that will be, rests for a time in that silence. The bottom of the world is not the end. It is the pause that holds everything together.